Okay, welcome to day 3, the final day of UCLA QC Biocollaborative Workshop 1C, Advanced Unix Scripting and Queuing for Large Data for Spring 2025. So yesterday we had a big fight trying to get bisulfite bolt installed on your guys' machines. We did end up with a solution for that, which was to use the virtual environment I already had and to let you just use that directly, make the files in my environment readable to you, and then you could just directly do your source activate from inside my place. So I have updated all the part 1, part 2, part 3 slide packages, all the copy and paste files, and all the files in my scratch copy of Hoffman to follow the method that worked. So these 2 slides are dead. This is the new slide. This is the new source activate command that will work. That empirically worked yesterday. And then, as I say, everything's been adjusted to follow this. So, and so we were only able to get yesterday to this point where we were just Q-subbing. We had done basically one test run of part 1 directly in the command line, directly invoking it. Actually, I guess that would have been at the end of the part 1 batch of slides. We did that here. So yes, so here is where we're just directly invoking it on the command line, not even in an interactive session here. And we got the statistics on usage for that. And then we moved to part 2 slides. And we talked about how that'll help us decide what the resource requirements are for when we actually run the 42 parts. And we kind of were just at the point of where we had described, we moved the alignment command into a shell script. And then we basically ended just with Q subbing that shell script into Hoffman. But let's just start here again. So this is basically the what it looks like to submit a Q job on Hoffman, and then we need to do 42 of these instead of just one. But this is basically the inside body of the for loop that's going to do the real work. So this is just some shell variables to declare the resources. Let's maybe try 2 cores, 7 gigs of RAM per core, 14 gigs of RAM total, 1 hour time limit. And then QSub takes parameters, and the most important parameters here are kind of explained in this little box. These parameters are just the way that you tell QSub about the resources that you want. So this stuff in black is the resource-related stuff here, and then this stuff in yellow is this stuff that's explained here. The most important one there is probably this -cwd, and that tells QSub that when it runs the shell script that's going to do your job, and at the end of the QSub line, we give the command line that QSub will cause to run on the compute node that it chooses once the job gets to the running state. And so that's this shell script for us. That's the one that we had just, that's this one up here, basically. Not select all, just this one up here is the shell script that actually has the alignment command in it. So the CWD means that whatever current directory QSub has, when you invoke the QSub command, it will propagate that current directory to this shell script. So when the job system starts the shell script, it will inherit the same working directory that QSub had when QSub was run, which is usually kind of what you want. Usually it makes the most sense most of the time. If you don't specify, so when QSub runs the shell script, it runs it in sort of like when you QRSH into a node, it's very similar to that. So it's like a new shell, just as if you were SSH into a login node or QRSH into a compute node. So what's that going to mean? It's probably going to land in your home directory, and it's going to have none of your environment, any of your shell variables you used to have set, well, they won't be set now. Any of the environment stuff like module loads and the Python environment, that wouldn't be done. And that's why in this shell script, we, for example, have to do the setup stuff that we do in our interactive session so that the script can run in the same environment we're used to in the interactive session. But we chose not to put any CD commands into our shell script. And that way the shell script works in more directories than just like hard coding it to one. You could hard code everything and that would work. But this way, sort of like this will just propagate the current working directory to the shell script. And as I say, if you don't put it, the default is probably your home directory or something. Same thing as any other fresh session gets. These are kind of more minor things not to worry much about. Maybe this one's a little interesting, the -MAS. So more letters can go here than just AS, but basically this says, send me email if certain things happen. You can have it like send you email when the job starts, when the job finishes, whatever, but eventually that's too many emails. So I usually only put on the weird ones. So like A is an abort if like the job is killed by the administrators or something real strange happens. I get an email and I forget which one is the S or whatever. Which anyway, AS is the one I usually use. That relies though on you having which email address does it send to? The answer is, oh, let me get on Hoffman and you should get on Hoffman too. Okay. And if you look in your home directory in Hoffman, now if you just do ls, you're not going to see everything because the default for ls is to hide all dot files. Every file name that starts with a dot does not show by default in ls, which is why I'm always putting the A, which shows the dot file. So if I do the -A, now you see all these dot files, and I usually like the long listing. So LA is always kind of my default for ls. But in here, you will see if I have a file called dot forward. And it's just called dot forward, all lowercase. And inside that file, it's a plain text file with a single line of text, which is the email address. And many programs, QSub, job system included, this is where they look to find out what email address they should send emails to if they're sending emails. So this is the address that receives the notifications from this -MAS stuff.
I want to change the email address. Is it possible for me to do after logging in?
Well, that dot forward file is in your home directory. You can put whatever contents you want in there and change it at any time you want. Yeah. Yeah, that's totally under your control. This is the job name. The job name isn't really critical what it is, but it does serve two purposes. First, when you do QStat and stuff and you like get listings of what jobs are running, the name does show up in there. You only get 10 characters in the QStat listing and stuff, but that, it helps. It gives you a little hint as to what job this is, as opposed to, once you get multiple things running. The other purpose it has is that some of the log files from the Q system do get this job name in them. So again, it kind of helps. So whether one puts a lot of effort into choosing nice job names or not, it kind of is up to you or whatever. But that's the two things that the job name affects. And then, yeah, so then this is basically just the command line that the Q system runs once it effectively QRSHs into the compute node where the job is going to run. And our shell script takes two parameters. Because the bisulfite bolt needs to know how many cores you want bisulfite bolt to use, because that's a command line option in bisulfite bolt, the easiest thing to do is to make this script take that as a parameter, because the place where we know that is back out here when we're about to do the Q sub, and we're going to have to tell Q sub that too, because we tell Q sub that here. So rather than have this number be split into two places and you got to keep it synchronized or something, it makes sense to pass it in as a parameter into this script. So that way, the only place you need to change if you want to change it is here instead of coordinated places. So that's that. And then the second parameter that the script takes is the fastqgzip file with the reads that need to be aligned. And then the way we wrote the script is that the script actually constructs the output file name from the input file name. So we could have made a third parameter be the output place where you wanted it if we wanted. We could have done it that way. The details here with base name and such are so that if we give an absolute path or some other path to the place where the reads are, the output file, the way we wrote the script, is always going to be in the current directory, the way we wrote this script. So that's sometimes that's useful because often when you start organizing your file, right now, like if you look at our uscratch W1c place, it's kind of getting pretty messy now, right? We got quite a few files here, and we could benefit from some organization. And pretty soon we're going to have to organize those files because it is kind of getting to be a problem. So that sort of helps that because this way you can have the input files in a different directory, but you're writing the output files to the current directory. So that helps with the organization because the reads you'll put in a directory, and then you want the aligned reads to be in a different directory. So this way, this allows us to decouple the input and output directories. So let me not bother running just this one job because we're about to run all 42. And so that will serve the purpose of seeing how it works in the Q system. So, and then I'll have to come back to this Q accounting thing because, well, I'll mention it now, and then we don't have a job right now to run it on. Although actually, I think the job system remembers, like, every once in a while, Hoffman goes through great resets and they essentially delete everything in the system, whatever, all the logs and stuff. But I think on the scale of months to a year, the job system isn't reset. And I think the Q accounting stuff is kept around that whole time. So even though this is a job I probably ran on Monday, the date should be here. It was the 5 May 11. That's 4 days ago. Isn't that Monday? Whatever it is, Saturday, Monday, or Sunday or Monday. Um, it probably does remember the job ID. So when I was making the slides and I did this one test part Q sub, and you see here, this is the job running, and this is the job ID. This is the serial number that the job system gives. Every job that the job system runs gets a unique job ID. It's just a serial number. It increases by one every time anybody on the system submits a job. And so this ID is the ID, the permanent sort of ID until Huffman Q system gets reset of this job. And one of the things the job system keeps is remember yesterday we did this like user bin time thing. Like when we did the test run, we did this user bin time -v, and that's because it gave us all these stats, and those stats helped us do things like learn how much memory this job took at peak, and like what was the CPU core usage and stuff like that. So the Q system actually automatically collects that kind of information for every job, and you can get at it post facto. So you do not actually have to take explicit action in the Q system to part two, yeah, to collect those statistics. You can get at them after the fact. So this is the job ID of like that little test job I ran on Monday, let's say. And so you just say Q accounting job ID, and then actually that was pretty fast. And this pulls back from its records. It has some list somewhere, some big table database somewhere, and it pulls this out of the records. And it has all kinds of information. It ran on node 6006. This was the job name. This was the current working directory that it started in. The job was submitted from node 7051. This is the Q sub command that did the submission. It was submitted at this timestamp. The job started at this timestamp. The job ended at this timestamp. It used this much wall clock time. This is related to the peak memory. Anyway, here's another indication of the peak memory, 12.8 gigs. So anyway, so you can get those stats post facto, which is often useful. And it remembers those for a long, long time. Let's see. Okay, so how do you do many of them? Well, we know about shell for loops, right? We know you can do for loops, right? And run some command repeatedly. So why don't we just put a for loop around the Q sub and submit them that way? And that is quite easy to do and actually quite effective for up to dozens of jobs. It's not too effective once you get into hundreds, and it basically doesn't work at all once you get to thousands. But this is, for a problem of the current size, which is 42 parts, this is a perfectly legit way of doing it. So I guess this was the point here before I do that. We start to organize the files a little bit. So let's organize this large. Get into your scratch space. Actually, I don't actually. I mean, get the rest of your environment set up too. So like, log in. You got to get a compute node, right? So get some. I'm on a login node too right now. So first, we're going to QRSH into a compute node. Yeah, so in terms of slides, we're on the part 2 batch right now, but we've already yesterday we did this command. We don't rerun that copy. You've already merged in the part 2 files into your thing. There is a part 3 additions that we need to merge in, but we'll merge those in once we get to the slide pack part 3. But we do need to get on a compute node, which we're waiting for right now.
That's really slow today. I'm waiting for last 5 minutes.
Yeah. There are good days and bad days. If it's really a problem, we can try dialing down the resource requirements a little bit. Like take the time down to 3 hours, take the number of cores down to, I mean, we sort of need this memory. So like, I don't know, 3 cores, but then you're going to have to bump up the memory to like, so this is 5 times 4 is 20. So with 3 cores, you could try 7. 3 times 7 would be 21. Anyway, if you play with if you're really, I mean, once you have one of these QRSHs waiting, don't kill it, just let it go. But you can open another login node session with other numbers and see if those work faster. And as soon as one of your sessions gets a compute node, that's great. You don't have to just wait until until you give up here and then try another one serially. You can have multiple QRSHs pending at one time with different resource requests in each one. Yeah, usually I don't have to wait long. While we're waiting, I can mention a few things about the queue system. So here I'm on a login node. QStat is how you list jobs on the system. QStat with no arguments shows you all the jobs on the system running and queued. That didn't look like much, but let's pipe it into less because it's actually gigantic. That's the top. The window's a little too narrow here you want to see them one line per job. So here you see job IDs, what username is doing it, the job name they have, where it's running. These R's are running. This is how many cores they asked for. And this task ID column we will talk about when we get to job arrays today. And this is page one. I'm going to hold down the space bar so we go page at a time. So we're out of the runnings. We're into the waitings. I'm going backwards now until we find the boundary. Yeah, these are still running. Okay, do. Okay, that's the last running. I'm going to hit the equal sign and Les will tell you where you are. You're on line 2659. So there are almost 2,700 jobs running on Hoffman 2 right now. And if you look in this last column, they have all kinds of number of cores, right? I mean, some of them, there's a 72 I saw. A lot of them are small ones. There's 256 cores for some of these jobs. And then how many are waiting? After this point, you'll see we reached the boundary. Oh my gosh, that QRSH is still waiting down there. So you see these QW queued waiting, and an H is an administrative hold. So one of the administrators has put those jobs on hold for some reason. Somebody's doing something they don't like. These are just QWs. This is the ordinary situation when you put a job into the system, but it hasn't found a place to run yet, queued and waiting.
It's QW can run in the future, but
yeah, so they're eligible, but the scheduler hasn't picked them yet. And you'll see some of these are actually big array jobs. So we're going to talk about that after we finish this 42-part for loop Q sub version. But how many jobs total? So we're now at the bottom of the list. How many lines was that? I'm now on lines, at the bottom of the screen is line 5445. So there's almost 5,500 jobs running and or queued, and it was like half running, half queued. But that gives you some idea of the size of the queue on Hoffman and how complicated the scheduler's brain has to be to try to figure out how to find a scheduling order for all these things to fit them onto their resource requests, given the pool of, well, from day one, we know about 800 nodes that it has to think about. Anyway, so the scheduler has to work. And this is also why QSub is sort of like, not like QSub doesn't finish instantly. All interactions with the queue system take a few seconds at least. And it's because it's a complicated queue. Well, we're still waiting down there, so maybe we got to change our resource requests. Usually 5 times 4 has not been a problem in workshops, but today, indeed, not going well. So let's try maybe 3.7, and I'm going to take the time down to, well, we're what? We're almost half an hour gone here. Let's go down to 240, 250. Oops, and then the second line here. Let's see if 3.7 shorter time is any faster to satisfy.
if anything gives up, do you still need to get the competition node, or whether you have submitted?
So QSub will independently, it could randomly land on a compute node that is one of your interactive sessions or not. It's just a completely independent business. It's going to find some node in the system that can meet the RAM and cores requests that you met.
No, my question is like if I submit some job as QSub, which may take maybe 12 to 10 hours, but my computational node won't be open for that long, right?
Well, when the job, so the job has its own resource requirements, which are independent of like your QRSH resource requirements. So when we do these Q subs, when we went like here, we did the one Q sub, right? So this is our first Q sub. So these shell variables, I mean, I could have just plugged them in directly, right? I mean, it'd be the same thing just to plug them in directly to this command line or whatever. But when we do this Q sub, the Q sub captures all these resource requirements and tags this Q entry. This, you see, it started too fast here, but this could have been a queued waiting job, and it maybe has to wait a while before it finds something. But this job ID has been tagged with all the resource requirements that it was told to use when the Q sub was when you did the Q sub and told Q sub what resources you want, it embeds those into the job ID, and when that job when the scheduler will schedule based on those job resources, and when the job runs, it will run under those resources. And each job can have separate resource requirements. I mean, when we do a for loop of 42 of these, we're going to use the same numbers for all of those 42. But these numbers do not have to be the same as our interactive session. Right? It's basically every job gets its own set of resource requirements, which are at least possibility of being independent of every other job. And nothing we're doing is telling QSub which node to pick or whatever. It's just going to do what it thinks is best.
Time, like here you mentioned 1 hour, but if
so that's a hard limit. That's the only real hard limit in any job. And so we are saying each of these, this job here, if it runs more than an hour, it would be killed. And actually, that's one of the things where the email should be sent to, because I think that's an abort. So I think the MA would send us an email. The job would disappear from your list. The running process on whatever compute node it will be killed, as if you were in a shell there and said kill whatever. So the process will stop. The queue system entry will disappear. You might get an email with the -MA. But whatever the files it was writing on disk or whatever, they're going to be in that intermediate state when it died, right? So that'll probably be a failure. I mean, you might have partial output or something, but in terms of did that complete and is that a useful output? Probably not. And you're going to have to detect that and delete those files. Or if you're working in a new directory, it doesn't matter, but you're going to have to rerun that guy. Probably with a bigger time limit or break it into parts or something, because you hit the time limit the first time. So although, as we said kind of yesterday, nodes kind of vary in how fast they are and stuff. And, if you think it's an outlier, like if you did 100 jobs and only 2 of them failed and the 2 hit time limits, but the rest didn't, your first try might be to just rerun them with exactly the same limits, because maybe that was just 2 slow nodes. And now the next time you run them, they just randomly go somewhere else and then they're okay. Yeah. But if you kind of try them a few times and they're failing every time, you probably should bump up the resources. If even with generous resources, they're still dying, then something's probably really wrong. Like the input data is malformed and something's wrong. And then you got to dig into it. But yeah, the first try is probably, even if it's a low % failure rate, first thing to do is probably just rerun them as is. We'll see that. We'll see that. So did we get a QRSH yet? No, ridiculous. Ah.
Yeah, I just got here,
Well, we've been waiting like more than 5 minutes for the QRSHs. Yeah.
Oh, I just did QRSH that line, but it's just QRSH. No.
Yeah.
Or you mentioned.
No. So this is the one I usually have in the slides. This is usually 2 minutes or something. I've used similar numbers as this for years. It generally works like 2 minutes for everybody. Yeah, I do think this week has been not a great week for Hoffman. I think actually, if you look at the you remember I mentioned yesterday, like that file server they had was like a few weeks ago or last quarter or something was having issues, and there was like that whole day it was dead or something or whatever. That's still on the news. Like you may not even realize it, but when you SSH in a Hoffman and you get the welcome message, you're supposed to sort of pay attention to this part, which is like the messages from the administrators. And like, here's the top message, Hoffman 2 cluster file system performance issues update. So if you say show news and you say like file system or something, you have to pick a word that's in the one you want to read. And they got the dates here. It was March 28th and March 31st. That was the badness there. And they say that their vendor for whoever supplies that it's like an 8 petabyte solid state disk of fast storage or whatever. The vendor said there was a bug in the software and they had some software update and they think they fixed it or whatever, but maybe it's not all fixed yet. Maybe we've got some ongoing performance issues in the network file system or something. So to their credit, I don't think I've ever seen Hoffman lose data. Like I've never seen files disappear that weren't deleted or corrupted or anything. I've never seen the file system to be broken. Of course, if you leave stuff in Scratch, eventually it disappears, but that's because the administrator deleted it intentionally. It's not a file system failure. Somebody told the file system to delete those files. So to their credit, I've never seen it lose data unintentionally or corrupt data or anything. But performance problems, absolutely. We've had performance problems. So, there we go. Finally got one. So, sorry?
Yeah. I got that.
QRSH with no specification, but then the resource, I think it's really small. It's like 1 core, 1 gig of RAM or something. It's so small. Now for some stuff we're doing today, that's okay. Because for example, up to now, we've been running like the aligner and all of our tools and stuff in our interactive session. But most of what we're doing after this point is queue jobs. And so that means that mostly what we're just running interactively now is like queue sub commands. Queue sub commands are not computationally intensive, right? You're not doing the real work. You're just adding an entry to the queue. Those you can kind of get away with on the login node. I mean, if you're going to queue sub in a for loop, like 100 of them, probably you should not do it in a login node. But like to kick off a random queue sub here and there on a login node, no big deal. So if we have to, we can get away with just, maybe you guys just can live in a login node anyway, because we're just going to be doing queue sub commands and there will be resource requirements in the jobs that get the jobs that actually work. And if that's any indication, those aren't going to be kicking off very fast today. So whatever, but you can still see the mechanics of putting jobs in the queue and so on and whatever. Whether we get jobs to finish running today is another question. However, I also give you pre-finished runs for all of our demos today. So like if you look in, like on day 1, you copied a big directory. On day 2, yesterday, I had you made additions to that directory, which wasn't as big. But when you did the copy yesterday, you got already cooked versions of a lot of the demos. So if you look inside your W1c, you'll see like these runs, slide prep and stuff like that. These are kind of runs that I did when I was making the slides like the weekend and Monday. And so you'll be able to see what the outputs look like, and we'll be able to have so like when we do like the sorts after the alignment and stuff, you will have the outputs from here. Even if your own live runs haven't gotten to the point where your alignments are done yet, you can use the slide prep outputs to try experimenting with the next stage here, because I've already given you copies of all the of runs that we're working on the weekend and so on. So hopefully you guys your QRSHs are still waiting. But even if your QRSHs are still waiting, leave them waiting, open another session, stay on a login node, and you can kick off some queue subs inside a login node. That's okay. Okay. Okay, so yeah, so like I said, we're going to just do the 42 now, because why just do a queue sub once when you can do a queue sub 42 times? It's all the same. So the first thing was we went off talking on things because we were waiting for the QRSHs. Now we got the QRSHs. So okay, so we were following slide 2 actually, and then slide 3, because after the QRSH is done, you need to switch to your Scratch directory. And if you're on a login node, then just do this on the login node. And then set up the usual stuff. So we might need SAM tools. Although as I say, I think we're doing everything in QSub, so we don't actually need SAM tools or BS Bolt to work inside our interactive session. But just in case. So that will activate SAM tools and BS Bolt. So now if you say SAM tools, that should kind of work. If you say BS Bolt, that should kind of work. Although, as we know, BS Bolt just printing help isn't the full test. You actually have to do an alignment so that it kicks off the BWA, because it turned out with Conda, the BWA was the problem and not the bisulfite bolt Python stuff. So that's not a complete test, but that's kind of working. And the reason why you got 3 slides today was because I went back and I changed everything to work with the solution that we found yesterday. So like if you look in the day 1 slides now, these 2 slides are X'd out, and this is a new slide that's got the new method, and then everything's been updated to use the new method. So okay, so okay. Okay. Okay, so we need to clean up files a little bit because our directory is getting a little like it's like 2 screenfuls now just to even list it. It's just we need to start organizing things like you would do it if you were really doing a project. So we had a bunch of like test runs that were sort of like maybe you got these, maybe you didn't, but like this was at the very end of yesterday. I did like part 1 as a test run, and then I also did part 2 as a Q sub test run and stuff. Let's just make a testing directory where we can throw those. So testing and what's going to go in there. That's the little guys here, like this part 1 that I already did. So it's this file, and then it's the part 2 that I did here. And there's like a BAM, standard error, standard out there. So let's put those in the test run. And what's the next thing to clean up? Oh yeah, then we actually have the original FASTQ files, but then we cut them down to the 10.1 million read head files, and then we split the heads out into parts. Let's move the unsplit heads into their own place. So I call that directory day 1 cut downs. And so that is the SRX star head FASTQ-GZs. And then I did the head 2 because I think I did them 2 different ways. One of them is probably with the fancy pipe viewer double progress bars or something. And did I do the random sampling demo live? Actually, I didn't. On the slides, I did the random sampling demo, but I don't think we actually ran that. So I don't have the rand samp version of these. So I only need to move. The head and head 2s. Okay, so that cleans up a little more. Let's move those random demos that we were doing. Like these were like all like little tiny demos we were doing like day 1 and stuff. Let's move those aside. So that is like what? Like this example 1 txt out. Let's get rid of him. I mean, or we could just delete them or whatever, but I like to not delete anything. I like to leave the directory in the state that we did it live. So if you want to look in there, you can see, like, if you want to go back and look at what happened, you can go look anytime you like. So that's all the rand 1 txt and the rand blah blah txt gzs. We'll put those in that day 1 demo pile. What else do I put in there? Oh, we did the word count 2 ways, right? Like we did I gave you the pre-baked out of the oven WCs, and then we did our own WCs. So why don't we move the redundant WCs we did into this place too? Maybe that's pretty good. Okay, so those all go into day 1 demos. Okay, that's a little better cleaned up. I'd like to clean up the part files as well, but the way this slide is written, that hasn't happened yet. We'll do that in a second. We're about to, in another slide or 2, we're about to move all these part files into their own directory too. So that will actually make this listing kind of fit on one screen and be more readable. But that's the last kind of cleanup we need to do. But this slide hasn't done it yet. Oh, and then we have this tree. I think that was where I was showing you like a find into xargs and gzipping like a huge set of stuff. I think that's this tree is that demo. Yeah, why don't we throw that in the demo piles too? It's not a day 1 demo, it's a day 2 demo. So maybe I'll rename that earlier. Maybe we'll call it day 1 and 2 demos. Whatever. Okay, so okay, so I want to do single q sub in a for loop and do 42 q subs. How complicated that becomes depends on how much we care about making the job names make any sense. So we could just give them all the same job name. It is not required that job names are unique. You could call every job you ever make A, and that would be fine. It's just not as helpful as it could be. So the purpose of these lines is to do a bunch of shell string transformations to construct a nice job name from the file names. So these are going to be the resource requirements for the jobs we kick off. 2 cores, 7 gigs of RAM per core, 1 hour time limit. We'll put those in some shell variables. This is going to be our for loop. The for loop is over all the part fastqgz's, which should be 42 x's here. And if I just do echo x, you'll just see their file names then, right? So I'll do the loop with just an echo in it, right? So there's the file names. There should be 42 of them. If I pipe it the word count and ask 42. Okay, yeah, so that's all good. But like what kind of job names do we want? Well, this is sort of like the sample ID, and then this is like the part number, and kind of it would make sense, like one nice job name would be something that has the sample in it and something that has the part number in it. But like you only get like 10 characters in like the Q stats and stuff, so you kind of got to smush it down. So this string transformation stuff is just kind of like, partially an exercise in showing you fancy string manipulation in the shell, but the reason why it's complicated is because we got to pick out the right, the bits of the file names that are relevant. I mean, this isn't really critical, but like this first one is going to strip away everything after the first hyphen. So this is like a typical file name that we've got here. So the first transformation is to kill everything from the first hyphen to the end, because that's basically the sample name. And then maybe we don't want the SRX at the front because that's the same for all the samples. So maybe we kill in the SRX at the front. The percents kill things at the back, the hashes kill things at the front. So this is a prefix deleter. Get rid of the SRX at the front. This is another suffix deleter. Get rid of the SE, which really stands for single end reads. That's the same in all the samples too. Maybe we'll get rid of the SE. And then we got to, that actually is the sort of the sample number, like 101.207. So that's now ends up in this shell variable samp short. And then we need something with a part number. So we start again with the original file name. We drop off the .fastq.gz. So this is the original thing. Drop off the fastq.gz. So now we got this thing. And then we got to kill the, we've got to kill everything up to the last hyphen. And that's what the double hash does. So find anything that ends in hyphen dash part. And the double hash means the longest thing you can do that way instead of the shortest thing. So that means the longest thing, hyphen thing you can kill is that. Okay, and in fact, the part is part of the thing you kill too. So basically that will just leave the O1 left. And so part num ends up just being the O1. And then we compose the job name as A, maybe A for alignment, and then the sample short name underscore, and then the part number. And so we end up constructing a job name like this. Whatever. I mean, if we don't have to do that. That's just, sometimes it's nice to be able to construct a nice job name. I just show it to you as an example. So if I put that in a for loop and just echo out the final job name, just to see if that works, there they are. And there you see the constructed job names from our file names. And then we're ready to basically do the Q sub. So just replace that echo with an actual Q sub command that does something interesting, right? So we're basically copying the Q sub command that we saw at the end of yesterday. So here is the actual Q sub command that we did as our first Q sub. And I'm just dumping that instead of this echo job name, I'm just dumping that here and making whatever minor adjustments there are. Are there even any adjustments to do? I guess there's, whoops, all that is exactly the same. This is the same, and all I did is where the file name used to go, I put X because that's the variable that our file name is in now. So our BS align one part script, which takes 2 parameters, remember, number of cores, which is a constant in this case, and then the file name. And the file name just comes to be whatever is the current iteration of our for loop. And so we can just run this shell for loop, and that's just going to call Q sub 42 times. So here we go. So normally a Q sub runs in a second or something, but there we go. Okay. You see the job numbers aren't consecutive. That means other people are submitting at the same, oh, maybe you guys. Right, but that you know the numbers are completely serial, and if you're up at 3 a.m. and you're kicking jobs in, you might get consecutive numbers. But when you see that you're not getting consecutive numbers, it's other people are sticking ones in their interleaved with you. Those job numbers are unique for the lifetime of the queue system, and the queue system only gets reset like every year or two. So they are very long-lived. No, this is the 8.87 millionth job that Hoffman has done since its last major reset. And I don't know if you saw the Q accounting thing stuff, but the system keeps stats on every job for basically a very long time. So like when we ran the single job, when I did slide prep and ran this single test job on part 1, this was the job ID, and that was like either the weekend or Monday or something. And if you say Q accounting -J and give a job number, even though that was a while ago now, you might even be able to do it even if it's not your own job. You might be able to inspect anybody's job. Like you can try this Q accounting -J with this number and see if it works and tell me. But certainly you can get accounting stats on your own jobs. And so even though this job is finished days ago, I should be able to pull its statistics back out anytime I like. And so this, like yesterday we did that user bin time and got stats on the test run. Essentially, you get that for free with every Q job, and it remembers the stats forever. So this is an example of using that job ID. Also, when you say QStat, or you say, you can say like QStat-U in your username. That's the long way to do it. That shows you all of your jobs. Let me see if I can get this one. There we go. So job ID is the first column. Name of the job is here. User, of course, that specify that show me only my jobs. State. Well, so what is this first one? This is my QRSH. Okay, this QR login name, that's from QRSH. This is my QRSH. And you see that it's running, of course. And you see it's running on node 6098, which is the node I'm on here. And I have 5 cores there. But you see none of my I have 42 jobs in the queue, and they're all waiting, queued waiting. Okay, so they're waiting to be matched up with resources just like our QRSHs were waiting. And you see the job IDs here. Those job IDs are also useful. For example, like suppose you made an accident and you've got to get rid of a job. A job is either going crazy or is stuck, or you submitted a whole bunch of jobs that you don't want to submit. Like you need to change your script, and like you need to kill the submissions currently and resubmit. QDEL is your command. So like if you could put a number here, and QDEL is QDelete. So that you put a job ID there, and then that job will be removed from. If the job is queued and waiting, it's no big deal. It will happen very fast. It'll just disappear from your list of waiting jobs. If it's running, it'll go to the node and it'll kill it wherever it is. If it's in the middle of something, whatever, it'll just get killed, and the files on disk will be in whatever intermediate state they're in and whatnot. But then it should disappear. So even if they're running, the QDEL will kill it and remove the job entry from the table. So we're kind of in a game now of just waiting for these to start. I'd like to at least see one of them start so that you can see the files, like some change in our file system. You notice that it's kind of like when we did jobs in the background on one node. I've got my shell prompt back and I'm doing other things, but my jobs are sort of running in the background, except the queue system is managing it and they haven't started yet, but they could start at any moment. But it's sort of the cluster version of the ampersand backgrounding, if you like. The Q sub is sort of like the ampersand for the cluster. So as soon as one of these starts, we'll be able to do an LS and see like some changes, because we should start to see an output file, some log files, something. But you know, we're in a situation where today Hoffman seems to be really having trouble. There's long latencies between putting a job in and getting it satisfied.
That stops.
That's coarse, basically. A shorthand for QStat with no arguments, that's everybody's jobs, which is like, as we were just looking at a few minutes ago, actually it's closer to 6,000 entries right now in the queue. The shortcut for qstat-u and your username is basically my jobs. It's just a shorthand. It's just shortened such type. So there you see the same list as I've been getting, but with the qstat. It's basically just a shorthand. So jobs is for your shell, and that's the backgrounding thing, right? It's a totally different thing. My jobs is cluster jobs, and it's essentially it's just a shorter way of typing this. So it almost makes me want to submit just some like tiny 1-core, 1 gig of RAM stupid jobs just so we can see something happen. I mean, normally, you know, on Sunday or whatever, I put these in and basically I had 42, all 42 running in like 2 minutes. So like on the slide here, you'll see like this was, well, what is it? You see here it's the 511. What is, I keep saying, so it's like 4 days ago. So wait, so Wednesday, Tuesday, Monday. Oh, it's Sunday. I guess it's Sunday.
Because weekends are better.
Yeah, weekends are a little better. 3 a.m. is even better. 3 a.m. on a weekend is good. Like Friday, like Saturday morning, 3 a.m., that's a good time. You can see I was up late, right? So that's actually, so this is Sunday morning. I was working late on Saturday, right? Because this is like shortly after midnight on Sunday. So, but these are all, basically I had all 42 running at once almost immediately. And that means that since I was asking for 2 cores each, that's 84 cores, not necessarily all on the same machine, distributed around. And the total amount of memory then is like 0.5 terabyte of RAM I'm using in aggregate across those. So it is substantial. And it was no problem. But today, we've been talking for 5 minutes at least, and zero started. Today's Thursday. I don't know. I think the clusters felt slow this entire workshop.
So for these one, you can't put 5s here.
You can't what?
You can put 5 viewer here.
I,
5 viewer, like we.
no. That's an interactive thing, right? There's no place to really. I mean, it would go in the log files if you did, but it's pointless. I mean, you have other ways of looking. You can just ls at the files and see them grow, and you've got other ways of monitoring progress and stuff. The PV is more for an interactive session. So I mean, I guess we're going to continue because, I mean, hopefully one of these kicks off. If you want to see what's going to come out, it looks like what's in your srun slide prep pass 1 directory. So if you look in there, which you should have gotten as a side effect of copying yesterday, this is what the output looks like from that kind of thing. So if you go into that directory, this is what the output looks like. So you'll see that there's a lot of log files, and these are named after the job names. So like this A101.207_01, that's one of our job names. And then you see EO, PE, and PO. That's the standard error, standard output, parallel environment standard error, and parallel environment standard output log files. And this is the job ID. Okay, so this is because as I say, the job name isn't necessarily unique. That's not enough to have a unique file name. So with the job ID in there, it's a unique file name for sure. So the parallel environments, you'll probably never see. These will always be empty, no big deal. But basically, this is the standard error and standard output. If your shell script or any of the programs it runs pushes stuff into standard output and standard error, and you didn't redirect them to other files, they will show up in these log files. And you see some of these, like the standard outputs are non-zero size, so there's something in there. That's going to be like, our shell script has those begin-end echoes, so that's going to be those. And then you start to see the outputs, right? So this is a BAM output. This is a BAM output, and there's a bunch of those. And then if you look at our script, we actually do capture the pipeline, the bisulfite bolt alignment standard output and standard error. We do capture those in separate log files. We could have chosen to just have not do separate redirection in our script and just let that mix in with the rest of the standard output and error. But just from practice, it's sort of I find it's more useful to sort of, as I say, separate out things that are kind of queue system level versus from things that are sort of analysis level problems. So for example, suppose your shell script was broken, right? So like you actually have like syntax errors in your shell script or something goes wrong in your shell script. The shell script I'm talking about is the so-called the terminology for this kind of script is a work script. Okay, this is a script that actually does the work of a part. If you had a problem in here, you got some typo in here or whatever, and that's going to cause an error or something. Well, that's going to produce an error from the shell, which will go to either standard output or standard error, and that's going to end up showing up in one of these log files up here. But if you've got problems down, like if bisulfite bolts start spitting out errors, because we put that in parentheses and then redirected that to our separate log files, those will show up down here in these log files. And I just find empirically it sort of helps to kind of like separate those out. It means that when you go to look at the Q system ones, it's more likely that those are going to be empty or very simple. And so that sort of already crosses off a whole lot of problematic problems at the Q level. Then you can go, once you kind of decide that the parts past those, that you can look inside these for analysis level problems. Also, we know bisulfite bolt produces like alignment statistics, like remember like the percent aligned and unaligned stuff like that. And so it's also nice to kind of like put those aside rather than mix that with all the other stuff too. So I think we're probably still waiting. I don't even have one started. Yeah, that's ridiculous. So we are going to look at this pre-canned version from Sunday or whatnot because we don't have a choice right now. So the main thing we have to decide right now. Well, why don't we? It's 2:30. Why don't we take a 5-minute break because we like to give you a break every hour, and also I will show you the QR code, which if things work well, all you got to do is hold your phone up towards the screen and it should take you. This is just a Google form that Eloy sets up, and it would be great if you could fill that out with feedback on how this workshop is and works for you and so on. That'll be great. And then I'm going to actually take a bathroom break myself. So I don't know if my laptop's going to go to sleep or not, but probably you've already got or you haven't.
Part of these slides, no.
No, I usually don't because the slides usually end up on websites and sometimes they go on YouTube and stuff like that, the videos and so on. So I usually try to not put the QR code in those. So Oh, finally. Well, you can actually see the delay there because the submissions are all at 2:19 and the starts are at 2:33. So we waited there for almost 15 minutes. When for jobs of this resource requirement, I would have expected almost instant. I mean, not instant, but like 2 minutes or something, not 15. Okay. Where were we? So we were going to inspect the output of this thing. So okay. So because we don't have the full set ready from our live run, although finally we do have something like, so if you actually look in your, I don't know if yours have started yet or not, but I can see in my W1c directory, we start to have some output. So first of all, you see I start to have log files because I've only got 4 that have started right now. So I've got log files from the first 4 that have started. You see some more log files from 4. You see 2 in progress BAM files. You remember we have that MV trick so that we do the BS bolt writing to an in-prog BAM so that only once bisulfite returns success do we move that to just be an ordinary BAM as help for us to decide whether the BAM file kind of is good or not. Although that's not the only way. I mean, you have to kind of check other things too, but that's if you see in-prog BAM and the job's done, that's a bad sign. I mean, it's definitely bad. These 2 haven't made an in-prog BAM yet, which either means that they have died already, like maybe they were short on RAM and they like didn't even make it that far, or they just are still loading, like BWA is still loading and it hasn't got to the point where even making the BAM file yet. Anyway, so it's been another 60 seconds since we looked there. Oh, that guy got an in-prog BAM. So maybe he was just still starting up and he just hadn't gotten to the point where he was writing his thing yet. This one's actually making progress, right? Because you actually see a non-zero size there. This has got a non-zero size. That's good. This has got a non-zero size. Oh, that one's 0 size. But I bet if we give it that guy a little time, probably he'll become non-zero. We could look at like what's happening in some of these logs. I mean, these aren't finished yet, so they could get bigger, but we see the kind of stuff we've seen come out of the aligner showing up there. And if we look at some of the logs up here, like this one, what kind of stuff is in that one? Oh, actually, one of them is supposed to be finished. So that's the echoes that are in our script. Like if you look back at our work script, that we've got these echoes in here, and that's to sort of let us know that our script actually started and the script hit the end. So let's see if job 1 did job 1 rename his BAM to be, oh, he did. So that's all good signs for job 1 sample 7 part 1. That's kind of looking okay. Same thing with this guy, probably okay. This one still 0 size. The other 2, at this point we can just do ls. Hello? I'm typing, but I'm getting nothing back. Okay. Always make sure, if there's something that makes your heart rate go up these days, it's like if your terminal session suddenly stops responding and you wonder if your internet just died or like whatever. And you might as well just do like start, like one way is to deal with the long listing like that is just focus on the files you care about most, like star.bam, right? So now we can kind of get a easier eye view. Actually, a part 5 started and part 4's got a non-zero size now. Part 3 hasn't yet. Anyway, you see how it goes. So, things are happening. things are progressing in the job queue. You see here that some parts have disappeared because they've finished, right? So part 1 and 2 are no longer in the list because they're done. Whether they're done successfully or not is the second question, but they are no longer running from the queue system's point of view. 3, 4, and 5 are running, and 6 onward have not started.
It aims can get something on that error, like something that job.
Job has to fail pretty weird to actually stick in the queue with an error. Normally they just disappear.
Those files.
Oh, the log files aren't going to go away until we remove them if we decide we want to. These are just files.
It's that E file should show some it shouldn't be non-zero. Right?
E files.
Like the one at the top.
Oh, this one? Well, it just depends on whether our script writes anything to standard error. So I don't think if things go well, anything will be in there because this echo goes to standard output. This echo goes to standard output. Everything that happens in here is redirected because like this is all in parentheses, and we redirect both standard output and standard error. So nothing can go, that's all into its own files. That leaves only this stuff as possibilities for where standard error could come from. And if no errors occur, we won't get any output, right? So like these are setting shell variables. This is calling base name. This is the module loads and stuff like that. Normally those don't produce any output on success. So if things go well, we actually expect the error files at the queue level to be empty. Okay, let's go into the slide prep pass 1 though, because that's after a full set has completed, and I can show you the general kind of checks that you want to do to determine completeness. Some of them you've already seen, basically. So, where I don't want to take too much time on this, and it is documented in excruciating detail on the slide and so on. So we could just sort of like, I mean, and the way you test for completeness sort of depends upon the problem, right? But in general, the kinds of things you want to look at are, it has to be 75% in this. The projector is such a small screen resolution that we don't even run the slides at 100% here. Normally the slides are just like a tiny corner of my main window, but now they're like bigger than the window. It'd be nice if we got a higher res projector. So some easy things to check are just like how many files are there, right? So like this is just accounting, like all the .os, .es, POs, and PEs in those Q system log files. We got 42 of them. So first question is the set of files even look like they're all there, right? Like a very obvious way something is wrong is if files are missing entirely, right? So we got 42 of all of those. How about the other sets? We've got 42 standard out, standard errors, but we only have 39 BAMs. So now we know there's at least 3 parts that are dead because we don't even have 3. We're missing 3 BAM files we should have. Let's ls everything that's got BAM in it. And what do you see? Oh, you actually see 3 of them are still marked in prog, but these died on Sunday morning or whatever it was, right? So those didn't make it to the end. And you see that one's only 28, 20. They're basically empty BAMs. I mean, if you kind of were to take a wild guess, you might guess what happened. It's going to be these guys died of RAM problems, right? So, but we don't know that yet for sure. But I'll tell you the punchline right now is that those guys didn't make it because they ran into memory problems. So we know now that there are 3 parts that need rerunning: 714, 8.1, and 8.20. Those 3 guys are definitely on our list of reruns, but maybe there's more. So the next thing to do, we've just checked file accounts. Now we're going to, this is looking at the in-prog business versus not in-prog business. So these guys in red are now definitely on our list of needs reruns. We can look at some of the log files now. The easiest test on a log file is just to look at their sizes. So the capital S and LS sorts them by descending size. So if we look at, say, like all the .standard out files and sort them by size, you see they're all 806 bytes, except 3 of them are 327 bytes. That already tells you sort of like these 3 are outliers, and you should look more carefully at them. Oh, and guess what? Those are the three that died. So no surprise there. It's picking up the same set, and we should look at the contents, but this is already another way you can sort of like start to pick out like outliers and guys that need focus and stuff like this. So we could look at the standard errors by size. And there's a little variation there, so we will look at the contents, but there's sort of a big break. You're like here. Well, first of all, there's these two, which are kind of a little bit outliers. Maybe that's okay, but we'll see. But definitely these three are more different. Or well, let's see. These two are smaller, but maybe that's not a big surprise because those are the 21 part 21s. Those are the 100K read instead of 500K final pieces. I mean, here's what's happening, right? Remember that the standard error is out of BS Bolt, and that's mostly log messages from BWA. And BWA does the reads in little batches, and it basically produces a bunch of stats information for every batch. So basically, the size of the standard error output out of BS Bolt is going to be proportional to the number of reads. And that's why the part 21s are small in the standard error logs. That explains why these two are here. Then the other three that aren't kind of like in the 1240Xs is these three. And those three are the ones that are dead, that didn't make it to the end. So that's kind of why the sizes of these logs spread out that they do. The real thing is to look at the contents. So that's actually what the next slide does, is start looking at the contents. So here we look at all of the .o files from the Q system level. A good way to look at large numbers of files is with more and then a shell pattern. So if you do that, you'll see that more kind of tells you it gives you a little header and tells you what file it is, and then it shows you the contents. If it was more than a screen full long, it would be waiting, but these are tiny files. So you do that, and then you can just kind of hit spacebar, and I'm just going to hit spacebar in key repeat mode and just get them all there. And now you can kind of scroll, and you're now looking at the contents of many files in a fairly efficient, fast way. And you can see that all of them just have the two lines from our shell script begin, end, and that doesn't show any problems at all. That level's okay. Another way, like if those logs were longer, another way to kind of deal with looking at like large numbers of log files is that you can concatenate all of them together, sort the lines because that'll group similar lines together, and then pipe that to less. I mean, here it's not going to be that exciting. It'll be a little more exciting when we look at the BWA standard error logs and stuff. But here, what you will see is all the begin lines grouped with all the end lines. And now it's sort of more like visually lined up, and you can kind of look for like outliers visually kind of this way. I mean, this two-line thing isn't a great example. You could also like count the number of times you get lines with begin. Like grep takes grep will pull out the lines with a begin in them, and then you could count those with WC. So we see there are 42 begins in that set of logs. So because I mean, in full generality, you could have 10,000 of these, right? And you don't really want to have to look at them all by hand, which is why you start using commands to like, try to find the guys that are problematic. You're trying to use more commands to figure out whether things worked or not, because you don't want to have to look at everything by eye. With 42, it's not a big deal, but with bigger sets, it starts to become a big deal. So we could also we know that the only lines we expect in those logs are begins and ends. So you could concatenate all of them, grep-v, which is everything but. So remove the lines with begin, remove the lines with end, and then what's left. You're not expecting anything left, but this would show you like if there were lines with error messages or something in them, they would probably come out from this because they wouldn't be the begin and end lines. So that's how that goes. You need the attendance? Or? Yeah. I don't think we did attendance yet.
Can you read some guide?
Yeah. Yeah, that's right. Yeah.
Was it on this? Oh, it's on. Thank you.
Okay.
Josh. Zhang. Josh.
I'm Heidi.
Heidi, sorry. Yeah.
Okay. So now we're looking at the pipeline level logs that we had done. We kind of isolated themselves. So again, we'll do a more on all the standard outs. Okay. And here you see that actually BS Bolt writes those alignment statistics to standard out. But remember, standard error's got all that BWA stuff or whatever. There's another argument for separating standard out and standard error, because like oftentimes standard error is like more progress information and errors and weirder things, and standard out is more like the stuff you're supposed to expect or whatever. So this kind of keeps the alignment stats kind of in their own files. So we now can sort of like scan and sort of look at the alignment stats kind of like pretty easily for each of these parts. And like, for example, like one of the numbers we might be interested in is mappability. We could just grep out like mappability for all of them, right? So like the file name patterns there. So we could grep out mappability for those. And now you see in a collected format, like the mappability across all those parts. And we can immediately scan that column up and down and say, oh, they're all about 93%. That looks good. But if you had a part that was like 0% or something, or 2%, you know that's a part you got something weird. So you got to check it out. So you can look at all the stats that way. Here, the cat sort is going to be a little more interesting. So you see all the different lines have been grouped together, right? So actually you see like all the unmapped reads have been grouped together, and it's like, oh, wait a second, looks like there's two outliers. But I guarantee you those are the two part 21s, all right, or whatever. We could verify that out, but that's why there's going to be two of them there. Total number of reads, 500,000, except there's two of them that are 100,000. That's exactly what we expect. So we can kind of go through this and kind of check each of the type of stats and convince ourselves that actually this all looks completely good. And we don't see any weird messages in there or anything. That all looks good. Then we should look at the standard error files from the pipeline, and that's going to be all that's BWA garbage and stuff. And this is actually one of the ones where it's sort of the sort thing is going to be one of the best to look at, because somewhere buried in here it could be error messages. Like it's hard to see. Actually, you see at the bottom here, actually that certainly looks like an error message or something, right? So the problem is that it's buried in so much noise that it's sort of hard to visually see. But when you do this sort of like cat sort less business, it's going to group similar lines together. And then sort of the unusual lines are going to be a little more obvious to see. So actually, it's kind of like these look like error message, like that looks like error messages. That's like something we should definitely chase down. And some of these lines look okay, like all that looks okay, normal stuff. But traceback, that's like a Python crash. So, something program exited strangely. That's normal progress from the aligner. Cannot allocate memory. Here we go. So that tells us to think about maybe somebody hit memory limits, right? And obviously it's sort of like node related or something, right? Because like 42 parts, 39 of them worked okay, but 3 of them didn't. So, but we gave them all the same resources. So anyway, but this points at the problem. Maybe you should consider increasing the memory for the jobs, or those are just weird nodes. And if we just try them again, maybe there's a our empirical rate of success right now is 39 out of 42, which is whatever that is, right? So it's 93% success rate, right? So if it really is sort of a stochastic thing, then pretty good chance, even if we just reran those, we might get lucky and get them to finish even with the same resources. That would generally be my strategy. If your success rate is pretty high and you have a small percent of failures, I would say first pass for rerun, just do the same thing again. If the second pass also fails, now try increasing resources. And if you do like a couple of rounds of resources increase until the point where sort of like you think it's very generous and they're still failing, now you got to dig into those parts more deeply. But so basically, if you sort of chase down all these things we've been checking, alignment failed, check out, all these times we're getting memory. We got 3 memory errors, 3 of these. We could chase down which parts are producing these various messages, and we would discover that it's exactly the 3 that are still in prog.ban. So we've now kind of done a fairly detailed check of all the log information we have, file sizes, everything. And we have concluded there are exactly 3 parts that need to be rerun: 714, 81, and 820. And so how would we rerun those? Because we don't want to just run the whole 42 over and over again and just hope that one of those times gets lucky and we get a complete set. We just want to rerun the ones that have failed. How is our main pile of 42? Oh, look at that. In the time we haven't been looking, only 2 are left. So that's not too bad. Let's see. So how would you rerun some of them? Well, you could do the same for loop we did. Well, actually one problem is that sort of like if we we have a choice to make. We could keep rerunning everything in the same directory and overwrite the ones that didn't work or so on. I would recommend mostly at this point that sort of like each time you do a pass, everything for that pass goes in its own directory. And then when you do pass two, those all go in their own directory and stuff like that. That just keeps the organization clear, and it kind of gives you a historical record about what you had to rerun when and so on. If you just sort of mix everything together, it will no longer be possible for you to figure out what happened at, a year from now when you have to write the paper or whatever. And you're trying to figure out if this is the good set of files or, which of these are good. And you just keep everything isolated and it'll be a little more obvious. So we could kind of just run a for loop again and just instead of giving the shell pattern that matches all 42 files, you just give a shell pattern with the files you need rerun, which maybe you don't use a shell pattern at all. And it's with three of them, you probably just list the three of them, right? I mean, you could do that. I'll show you another alternative though, which is to package up the qsub command into a shell function. So here I've just basically taken the qsub command and just wrapped it in a shell function. The shell function takes three parameters, which are the resource requirements. So the task n cores is now the first argument. The task per core gigabytes is the second argument. The job name is the third argument. The fourth argument is the file you want to redo. And the 1 hour, I just decided to hard code into this shell function. And then here's the qsub command, which is exactly the same qsub command that we've always run. And I guess the other decision I made is to give a absolute path to the shell script. So this is no longer assuming that the bsline one part shell script is in the same directory that I am in when I start qsub. Okay, I've given an absolute path to the shell script. This means, in combination with the design of that shell script, we were very careful in that shell script to not have any assumptions about what the working directory was when our work script runs. This now means I can run this function from anywhere. And we can put an absolute path into the input file names. And the way it's designed, our work script is designed is it always dumps the outputs in the current directory. So I can now do the following things. I can move, say, all the input files into their own subdirectory to keep those isolated. I can move all the pass1 stuff into its own directory to keep those isolated. I can make a new pass2 directory, change into that, and then kick off this shell function with the three parts I need run with absolute pass pointing to that new input file directory, and it will write the pass2 files into my new pass2 directory. And then if we needed a pass3, we could cd ... move up a level, make a pass3 directory, cd down into pass3, run this shell function again with the parts that failed a second time, and keep doing passes until we get a complete set. And so that's what this is about. So let's load up this shell function. Okay. And we've got to clean up a little. So let's change back to the top level W1c. Now, is my run complete now? Yes, I no longer have any. The live alignment jobs that we have done today are done. We haven't decided yet whether those are complete or not, but let's move them into their own directory before we do that. So I'm going to make a directory called sruns live pass1. So the ones that you have from the copy are called slide prep. The ones we're doing live, those are the live versions. So sruns live pass1 is the ones that we just finished just now. So we'll make a directory for where those can go. And we will move all the files that are relevant to that into there. So that's all the A star logs, the EOPEPOs, the SRX BAMs, the SRX standard error and standard outputs, all of those are going into this pass1 directory. Okay, so that pushed up all there. And then we're going to also isolate the input reads because it's high time for us to do that. So that's all the SRX head part blod fastqgzs. We're going to put in an sruns inputs directory. And now our top level is actually like readable for the first time in a long time. Okay, so you see here in our inputs directory, that's now just the input files. And in the live pass1 directory, we have the batch that just completed. And we're not going to spend time to isolate, do all the checks that we just did, but let's do an easy check. Let's sort the BAM files by size. Those look all probably pretty good. This guy is small, but he's a part 21. So that's okay. But these are empty. These are also the only in prog guys. Today we have 5 that didn't survive pass 1. These 5 are the ones we need to rerun and so on, because we did not get useful BAM files out of there. So let us make a pass 2 directory, live pass 2. And then I'm going to CD into live pass 2. Okay. But now I just need to kick off the guys that need redoing. Okay. So the order of arguments is cores, RAM, job name, file. So we did pass 1 with 2.7 as the cores and RAM. Let's just try literally rerunning them. So 2.7, and then we sort of need the job names. Make up whatever you want, right? So we could do like, this is like second pass alignment. Which are the guys that need it? It's sample. They're all sample 8, I guess. 8, 8, 8, 8, 8. Yeah, they're all 8s. And then we need part 9. And then we need the input file for that. The input file is relative to the directory I'm currently in. I could give an absolute path. That would be one way to do it. But let's do it as a relative path to where I am now. So this would go up 1 directory, and then we have to go into the sruns inputs directory, and then they're in there. So it's sample 8, and we're heavily using tab completion here, and it's part 9. So that's the input file. But now, like, look how easy it is to queue a job like that right now, right? So this is our shell function running qsub for us any day. Okay, and there's a new job has been added to our list. In fact, we can now make like a little, so they're all sample 8. And the other parts I need to run are 12, 14, 20, and 21. We could do a tiny little for loop here. 2.7 for the resources, A2 underscore 8 underscore the part number for the job name. And the input file would be the 8, go to the right directory, and then the part number is X. And then we're done there with the loop. And there are my 5 parts of the queue, one of which is running. And since one is running, you can see here that in this directory, my pass 2 directory, I'm already starting to get the outputs related to pass 2 of the guy, the first guy that needs rerunning. Okay. Now we're not going to, we need to move along. So I have in slide prep pass 2, you have a copy of on Sunday or whatever it was, my pass 2 for my Sunday pass 1. And remember, my Sunday pass 1 had 3 failures. And so in my slide prep pass 2, you will see log files for the 3 guys that I needed to rerun then. It was 714, 81, and 820 back then. And now you see a new set of files. You go through the same steps of deciding whether these are complete or not. But let's not take the time to do that and just tell you the final decision, which is that 2 of those succeeded and 1 of those failed again. So we now have 7.14 and 7.1, or 7.14 and 8.1 have been recovered now. But we had 8.20 has now failed twice. Okay. So what we do then is we have to do a slide prep. What I did then is a slide prep pass 3, and I don't know yet whether we need a live pass 3 yet because we haven't got our pass 2s to finish yet. So this was the 3rd round on Sunday, and 8.20 has to be redone again. And this time, I think I ran it with more resources. I gave up trying to rerun with the same resources, gave it more resources, and this time 8.20 succeeded. And so now between my 3 passes, I have a complete set now. They're not so nice to use because they're scattered in 3 directories, and that's the immediate thing that we do next to fix. But that's how you kind of do multiple rounds and recover the guys that haven't failed, that until you failed. Yeah. Okay. Sorry. Yeah. Sorry. Car trouble is always nasty. All right. Okay. Oh, they're all running at least. So that's back in our live pass too. These should only take like 5 minutes or something to run in normal time. So we will know soon whether we need them or not. But let's proceed to explain how we deal with the fact we now have scattered files. The winners, let's call them the winners. All right. So we now have a pass1 directory where most but not all of the files are good. And then we have a pass2 directory that where sort of like those override things in pass1. And then we have a pass3 that overrides some of the things in pass2. And so sort of we want to be able to assemble a final set of files by the last pass that something appears in is the one to use, right? So like if something appears in pass 1 and 2, you need to take the number 2. If something appears in pass 1, 2, and 3, you need to take the number 3 or whatever. So we would like to assemble a new directory which has the winning versions of every part. One way to do that would be to literally copy or move the winners with lots of CP or MV commands. But that's not great for two reasons, right? First of all, if you use CP, you're using more disk space, right? You have too many copies. We're trying to avoid extra copies of things, and CP is just going to make another copy. You could say, well, what after you do the CPs, why not just delete all the pass 1, 2, and 3? I also don't like doing that because, again, I like to sort of have a history of what happened, and I don't like to delete the history. So, and I don't want to do the MV because that also kind of destroys the history, right? So you could just pull out the ones and collect them in one directory, but now the history is not reflective of what actually happened. So the question is there a way to sort of make like a virtual set of files that are copies of the real files, but without using the disk space of a real file? And the answer is yes. And the easiest way to do that is called symlinks, which probably is not a Unix feature you've seen yet. And I'll show you what the symlinks look like, and then I'll show you how we made them. So in the slide prep winners symlink directory, you have the virtual assembly of pass 1, 2, 3 winners, so that only each part has exactly one file in this winners directory, and it's the last pass that has that part, meaning that's the one that succeeded. So if you go into that directory in ls-la, and maybe I got to make the window wider. Yeah, I probably didn't. So I don't know if I can make the window tall enough. Probably not. It's 42 and then just with this font size. But this is what it is. So this is probably an LS directory that you have not seen before. But you notice that the beginning letter is now an L. You've seen dashes there for ordinary files, and you've seen T's there for directories. Well, L's are for symbolic links. And then you see what this is the file name of the symbolic link, but then you see this stuff you haven't seen before, which is like an arrow to something else. And symbolic links are basically things that look like files, but they're really pointers to other files. And so, and they don't take any space. They take only space. The only space they need to take is the name of the path name for where the target is. So basically, this is saying that in this directory, there is a file. It happens to be a symlink called this. But anything that manipulates this symlink, the real file it's going to deal with is this file. Okay, so it says when you come here to this file, no, you need to go here. Okay, so what you have to do is you have to go up one level from the current directory and then down to slide pass 1 and then down into this guy. And what you see here is that the pass number is changing, right? So like for most of these, it's pass 1, but once in a while, like here's the guy, right? So here's part sample 7.14 is pointing at path 2, because that's where we got success for that part. And down here, you'll see, for example, sample 8.20. So Safaras, are you doing dishes?
Yeah, I'm sorry.
maybe mute if you have a question,
My
unmute
bad.
or whatever. But thank you. So 8.20, we didn't get a success until pass 3. And now you see we're pointing at the pass 3 file. If I try to look at any of these files, like I could do like samtools view or whatever, that's samtools view on a symlink. But this works, whoops, less isn't spelled that way. But it works just like it would be if it was the file that we're pointing to. But so the advantage though is that these take no disk space, right? So you see the file sizes are like 71, and that's because there's like 71 characters in this path name that is the place where you're pointing to. So this basically uses no disk space. It allows us to leave the past 1, 2, 3 directories as they were, it preserves the history. But this is now a very easy directory to use with further shell scripts and passes and stuff, because further parts of our pipeline no longer need to know which alignment path the right winning file came from, right? It's now as if we virtually assembled sort of like a single run of 42 where every one of them succeeded, right? So this is a nice way to sort of organize the files. The only question now is how do you build this thing of symlinks? Okay, so that is probably the next slide, I think. So we figured out, this is the discussion about how you do the multiple passes. So the point where we're at here is called marshaling the winners. Okay, we're arraying, like in military formation or whatever, the winning BAM files. So here is the little shell blob that is doing that. So you would create the new directory where you want the symlinks to live, like sruns live winner. Actually, is our pass twos done? Is our live pass twos done? Yes. And then did the pass twos all work? I think based on our chances today, the answer is going to be no. So we don't yet actually have a full set. Oh, maybe we do. Actually, it looks like they work. So 1, 2, 3, 4, those look good. This one is short, but remember he's a part 21. So actually it looks like we do have a full set in 2 passes today. And I did not change the resource requirements either. So that shows you the non-determinism of success even under same resource requirements. So actually we only needed 2 passes today. Our split is like 37 and 5, whereas the other one was 39, 3 and 1, 39, 3, 2 and 1. So we can try this here. So we make an sruns live winners symlinked directory, and we change into that. Or actually, we're going to run this for loop actually from here. So we are pulling things in from the pass 1 and pass 2 and making symlinks in this directory, and we're going to do it all from the W1c directory. We could do this with a CD being anything, but we just would have to adjust various paths. But this is the way we're going to do it to match the slide. So there were 2 passes today to merge. So for pass in 1 and 2, do. And then in each pass, we're going to loop over all the BAM files that exist in that pass. Okay, so we loop for X in everything in the sruns live pass current pass directory, everything that ends in bsbolt grc h3 ends 114.bam. In particular, that would not match in prog BAMs. Do. So now we are in a double loop. So we once for each pass, and in each pass, once for each non-in prog BAM file. We do the base name thing so that, because remember, these X's then are going to have, they're going to have the directory name in them. So they're going to have this part plus the file name. I just want the file name part right now. So we make an fname variable using the base name trick to extract out just the file name part. And then we remove any existing symlink in the symlink directory. Now in pass 1, there's going to be nothing there yet. But the idea is that if pass 2 has things that overwrite pass 1, the pass 1 loop is going to make symlinks to everything that pass 1 had. But if pass 2 then has things that override that because we reran some of those parts, in our case, actually, it's not going to be a problem because everything that failed in pass 1 was in prog. But notice, for example, on the Sunday run, pass 2 had 2 in progs and 1 non-in prog, and the non-in prog was still dead. So actually that opens up a question, because then it means somebody lied, because we only do that MV of in prog to non-in prog when things declare success. So it actually means that bsbolt declared success so that way our MV happened. That must have been what happened. But it wasn't a success because the file was empty and there were problems, memory problems. So that brings up a question like, why didn't bioinformatician declare a non-zero exit status? But that's a separate question. But so on the weekend run, you can't rely on in prog versus non-in prog as a reliable indicator of success. Today, it just happened to be that we didn't have that happen. Today, everything that failed is an inprog.bam. It's kind of random. So in our case, we're never going to have the problem where we have to delete a symlink and replace it by a newer symlink. But on the Sunday run, that is true because the pass one is going to make up like the pass two is going to make a symlink say to that guy that's not an improg bam, but still a broken guy. And then pass three is going to have to replace that symlink with a new symlink. And that's why we have the RM here to delete any existing symlink because we're about to override it with a more recent pass. So in our case, the RM is not going to activate today, but on the weekend run, it will. And then this is the command that creates a symlink. So ln, it says link, and the -s means symlink, and the -v makes it just verbose, where it just prints a line of thing that says I'm making a symlink from here to here. And the way it works is that the order is target and source. I'm sorry, it's the other way around. Let me put it this way. The second argument is the new symlink that gets created. The first argument is the path that the link should be to, from the perspective of the directory that you put the new symlink in. So the symlink we want to create is in the winner's symlink directory with the same file name as the file name it has in the pass directory. But the target of that symlink relative to the winner's directory is you have to go up one level and then go to the sruns pass / file name place, which is our X variable in the for loop. So that's how it works. So where am I copying? I got the F name line. I don't have the RM line yet. Okay, and then no, symlinks can be absolute paths, and then it doesn't matter like what the directory is and so on. But if you choose to use a relative path, the target of a symlink is always interpreted as relative to the place where the symlink file itself is. So in particular, it does not matter what the current directory is when I run this ln command. The current working directory for ln only matters in terms of where this symlink is going to be placed. But in terms of how you phrase the target, you must phrase the target relative to where you're placing the symlink because that's how it works. If you think about it, it's like the only thing that makes sense. I mean, it's like it's hard to do it any other way. So that is us building all the symlinks. And you should see like these are all the pass ones, and then you see here are our 5 pass twos. And so now we have this live winners symlinked, and you see our full set here with some of these are from pass 2. And if we count how many files are in there, it should be 42. Yeah. Okay. So that is how that goes. Okay. So, all right. So, all right. So now I have a decision to make. So I would say to really finish this application, we would need to remerge the parts and then sort and index them. How you merge the parts depends upon the bioinformatics problem that you have. So for us to merge multiple BAMs, it's SAMTools merge is one way to do it. If it was like plain text files, like suppose we were making FASTA files, like suppose we were doing FASTQ to FASTA conversion of all these files, the way you concatenate FASTA files is just with like the Unix cat command, right? You just stick them together. There's no fanciness required like with BAM files. So you can sort of see already how to do that, but it's sort of like it just depends on the details. And to really finish our whole process of split, do something merge, we should do that. But in a way, that's the less interesting part than the part that I want to get to next, which is the job arrays part. So I kind of want to get to the job arrays part. And since we're kind of possibly going to run out of time, I would say we skip the assembling the results for now, move towards getting the job arrays part, in particular, like this template that I want you to be able to use to kind of set up jobs in a very flexible way that also scale to very large jobs. And then if we have time at the end, we'll circle back and we'll actually bother to do the reassembly of the parts here. And you do have the slides for reference if you actually care about this particular problem and how to reassemble. I think that'll be more interesting for you than us just sort of plowing through and possibly only being in the middle of job arrays at the end of the next hour. So okay, so we also have 10 minutes before the next break. So let me skip this slide, which is to well, the plan for how to finish this particular problem is SamTools does have like a SamTools cat, which sticks BAM files together. But then to use BAM files in downstream software, they almost always have to be sorted, meaning all reads on the same chromosome are grouped, and then by aligned position on the chromosome, they have to be left to right in the chromosome. And so you would have to do a SamTools cat, which would be relatively easy, but then you'd have a gigantic SamTools sort to do because they would already be grouped together then. SamTools sort, how does it work? It's going to basically have to split the file back into pieces again because the file is probably not going to fit in RAM. And so it's going to have to immediately resplit the file, sort the pieces, and then re-merge the sorted pieces. So for us, since we already have them in pieces, it makes more sense to do it a slightly different way, which is to do SamTools sort on all of our aligned pieces and produce the sorted version of each aligned file, and then do what's called a SamTools merge. SamTools merge requires the input files to already be sorted, but SamTools merge is way easier and more efficient and low RAM and faster than a SamTools sort. Merging sorted files is very easy. So like, think of it this way. You've got 5 files which are sorted. Okay, how do you produce a single sorted output that's the merge of all of them? Put your finger on the first line of each file. Okay, look at those 5 lines. Who is the first one in your ordering? Maybe it's this guy. He is the first line of the output. Move your finger down one place in that file. Repeat. Your fingers will sort of slowly ooze down the files in different orders, but you will be picking out the output as you go. And you only have to have in your memory one line from each file at a time to find out who's the file with the next one. But you never need to look beyond the current line in a given file because those lines come after the line you're pointing at in that file. So you see how merge of sorted is an easy problem. Whereas if you have to sort a big guy, you can't do it until you've seen the entire thing, right? Because you don't know what the first line of output is until you reach the very bottom of the file. Because that very last line could, in the sorting order, beat every line you've seen before, right? So there's no way you can produce even the first line of output for sort until you've seen the entire file. So in a way, then you have to compare everything to everything in some form. So sort of big things is hard. Merge of sorted things is easy. And so the SamTools merge is a very easy, fast, efficient, low RAM operation. And
unstated FASTQ files, the BAM files still need to be sorted at the end, right?
SamTools sort will do the right thing. So SamTools sort, it uses some default amount of RAM, but you can also tell like, oh, I put you in a job with 20 gigs of RAM and you're allowed to use 20 gigs of RAM. And what SamTools sort will do is it will read into memory until its memory is full, and then it will sort that chunk. And if it's reached the end of the BAM file, fine. I mean, it sorted it in RAM and it can just dump it out to the BAM output. But if it's a big BAM file and its memory isn't big enough to hold the whole thing, it will then have to write the sorted piece, the sorted chunk that it just did to disk. Then it can work on the next chunk, and disk is now accumulating sorted pieces, and then it does the merge afterward. Since we are already in the situation where we have pieces, it just makes sense for us to do the sorts on the pieces we already have and then do the merge, rather than the cat and then have sort resplit it out. It's just sort of going to end up being more work. It's going to be faster, more efficient to do it this way. So our plan for the finish is SamTools sort each piece. That'll be 42 more jobs. Then a SamTools merge, which will only be 2 jobs, because that's now that's a transition from per part to per sample. So the SamTools merge is only 2 jobs. And then there's a SamTools index, which depending on how you want to do it, you could do kind of in the same 2 jobs that you do the merge. The index is not really a heavy operation. It's a pretty lightweight operation. But logically, the SamTools index is another 2 jobs, because then that gets applied to the 2 big BAM files that come out of the merge step. So those are sort of the 3 commands that need to run. And we just need to make like a little a work script for those guys, and then a little shell for loop to kick off those guys. In fact, actually, I think the sorts are kind of small enough. You can even kind of do these 42 in an interactive session, and they're pretty fast. So I don't even know if I did them as Q jobs sort of in this demo. Probably, I actually not really. So, and so on. But anyway, and then the merges are here. The merges are a little more interesting because it's you have to kind of go, you're making a transition. You're not really operating on per part anymore. It's like, and so on. But like when we do the job arrays, we're about to kind of make these slides obsolete anyway, because we're about to do them the job array way, which is kind of better in all respects. So I'm happy to like not do these this way and just immediately get into job arrays. We got 5 more minutes before the break, so we can finish this up. Like this, we're about to get a job arrays. That's like right. It's basically the part 3 of the slides is the job arrays part. So maybe we can get these things talked about in the next 5 minutes and then take our break. So one question you may have had is, what if we had just done pass 1 with more resources? What would have happened? So I did that experiment. If we had time, we could do it live. So I did the same thing we did in pass 1. I just made a single character change. I increased the number of cores from 2 to 4. Okay. That also, because of the way our scripts always work, with they multiply cores times RAM, that also has the side effect of going from 2 by 7 equals 14 gig of RAM to 4 by 7 equals 28 gigs of RAM. And guess what? Well, 2 things happened when I ran this on Sunday. I didn't get as many of them running at the same time as I did with 2 times 7. They took longer to start, but none of them failed. It was success on the first pass. So was that a win or not? Well, this whole job only takes like half an hour to run from one side to the other, not a big deal. But if you had a big thing to do, then you kind of empirically have to figure out whether that's a win or not. Like, is the trade-off between fewer running at the same time and longer waits for them to run worth it to not have to rerun any versus letting a few fail with less resources and cleaning up after it? And the problem is, though, is that as we kind of talked about yesterday, I think, to one of your questions, even high resources are not 100%. They're never 100% guaranteed things are going to work. You always have to do the checks as to whether all the parts are good and possibly handle the cleanup. You do have a knob with the resources to control the probability that that happens, but the probability never hits 1.0, 100%. So it means that like it doesn't really make sense to try to just like crank the resources up and just like assume that's always going to work. At some point that trade-off is just not worth it. You've definitely hit the point where like you're waiting too long and too little is running at once, and it's still not a guarantee anyway, because it's never a guarantee. So you got to kind of play with things to kind of just. So the other hint was that, remember when we've done the stats and we've looked at the Q accounting, QACT, and we did the user bin time stuff. What was the number? It was like 12 or 13 gig was like what the test run wanted to run. And basically our 2 by 7s are 14, and it's just too close. In a way, I kind of chose the 2 by 7 for these demos because I kind of wanted to have some fail, because then I show you how you do the multi-passes and all that stuff. And if they always just succeed, then it's not a good demo for that. So that's why I start with the 2 by 7 and intentionally be so close to the line that there's a decent, a chance of failure, which we saw today. And Sunday, I also had failure. But it's like, we're still getting like 95% success rate or something with the 14. But the lesson is probably 14 is too close, right? You should probably run with 20 or something, right? That would be better than cutting it this close. Okay, so all right, we've only got like, this is a bonus slide, which if we had time, that would be fun. We don't have time. You can look at that if you're interested on your own. The last slide before the end of chunk 2 of the slides is this slide. And all this slide does is show you a third way of kicking off the Q subs. We've done 2 ways so far. We've done directly typing the Q sub in an interactive session. That was the first way we did it. The second way we did it was to put it in a shell function. We put the Q sub in a shell function. that was so that when we did like the pass 2 and pass 3, it was quite easy to write the command line to kick those off. The third way of doing qsub would be to put the qsub in a shell script and write that to a file, like a file called whatever I called it here. I called it submit.bash or whatever. And I made another directory to do these in. So like I guess in the slides when we do this high resource pass 1, those end up going into a directory called runs HR for high resources. You've got a directory in the copy that gives you the slide prep version of the high resource run. So that was like a high resource first time. And then this submit with a script thing is doing the high resource run a second time. So that's HR2. And so we'd make an HR2 directory. And then since we're in that directory and that's already isolated, I just called the script submit.bash because it's already isolated in its own directory. It doesn't really need a fancy name because it's not mixed in with tons of other stuff. And all we do here is we basically just put the qsub thing into the shell script and the for loop and the qsub right into the shell script. And we put the resource requirements in here. It's basically just the commands we would have run in the interactive session directly. I think I changed the way the job names work a little. No, maybe it's the same pattern for job names. Anyway, all that does then is then when you kick this off, you can just say submit.bash. So there's no difference in difficulty or anything with this. And there's not really like, well, why even do it this way? I'll tell you the main reason to do it this way is that because it immortalizes the commands you ran into a file. So if you think of like, the wet bench guys always got to keep a lab notebook, right? Where they keep track of everything they do. You as bioinformatics people should do equivalent things. How you do that is up to you. Like, do you have a running plain text notebook and some text editor or Microsoft Word or GDocs or something where you're writing your history, your daily journal of what you're doing? Or are you leaving files on all your directories that actually are literally like the commands that you were running to produce the stuff here or whatever? Well, the advantage of making a shell script file like this is that you made it a durable artifact, this file submit.bash, which reproduces the analysis that you did at that time. It's sort of a way of keeping a bioinformatical lab notebook, right? So it's not the only way to do that. If you did the shell function way or the direct way, hopefully you're keeping track of that somewhere else so that you have a record. But depending on your discipline and how you just like to manage things, maybe the shell script way is just the way you like to keep track of your records and notes and stuff. So anyway, so that brings us to the end of the part 2 of the slides. And we're going to take a 5-minute break for the hour. It's another hour. And then we are into the part 3, which is the job array thing. And this is going to have us develop a very nice system, and you'll have a template. This works for small jobs, big jobs, gigantic jobs, simple jobs, complex jobs. This is a very flexible system and quite nice. And so we'll cover that when we get back from the break. And then do you guys need the feedback QR code again? Or I'll leave it up for the break. Curious, what do you do for like keeping records of like how you conduct analyses and things?
So I do mostly using that text file to write the commands.
So you keep like a window open and you just kind of copy and paste things into there.
These things, especially that's whatever I'm doing the Hoffman cluster for our
So it takes some discipline to like keep that in sync with what actually happened. Yeah.
Yeah, so I mean, I guess it's easy to document things in R. It's a more organized system. But yeah, for all those Unix stuff, I'm not sure how to. So I think it's better to put it in a
Shell script.
script.
Yeah, because then your node file just has to say run the script, or even if you lose that, eventually you go back to the directory, you see the script there, and you can kind of figure it out. Yeah. There's sort of always this tension between making things easy to change and sticking them into files that make them records of what it was. So for example, like you see some of the times, like when we do the shell function, we have the resource requirements as parameters. That makes it really easy to experiment with like increasing the resources and so on. But there's going to be no record of that if you didn't keep a record somewhere else. Whereas the shell script, it's kind of embedded in there. So harder to change, less convenient to change, but it's a more durable record automatically. There's always this tension between sort of like flexibility, rapid iteration, and recording what you're doing.
Like Python, like Python notebook is kind of a good way of keeping records. And some people use OLAP. I'm not very familiar with that. But yeah, those are like
yeah, things with notebook interfaces, it's kind of easier, right? Because you can just mix the notes in with the code, and even the like graphs and stuff would just be all mixed in there. It's very nice. Yeah, it's actually one of the reasons why I like Mathematica. Mathematica's had a notebook interface for like since the beginning, like 25 years now or whatever. It was the first app I think that ever had a notebook interface. And in fact, when Jupyter and stuff they basically copied the GUI out of Mathematica and stuff and so on. So since I come from an old time, then I'm sort of into mathematics. That, you know, I did find that very appealing. Yeah, this whole mixed notebook where you have everything mixed together, it's very appealing. It's just I'm always going to be on Mathematica now because I've been there too long, and it is my preferred world. So
it's just easy to document things. You don't have anything to look back. You can just open them up, and like it's more like writing on a.
So Heidi, what are you doing for like lab notebook or keeping notes of what you do? Or
I use Notion.
I don't know what that is.
Notion is like I think it's use Obsidian, which is kind of a more offline version of Notion.
Is that a cloud-based thing? Or?
Kind of. It's like a note-taking thing to make code plans. So
it's more.
It's like a note. It's like a notebook, but it's more like neutral. It's more neutral. You can like paste any kind of.
yeah.
It's not like a live computing environment, but it looks kind of like a notebook.
Yeah. So like I can write the hashtags and then like also write.
Can you share with others like using?
So where is it stored? Is that a web service? Or?
This is I think a web service, but then it has like a desktop.
So you also have like copies on your machine of these, or you can make like PDF. Could you export these if you want? Yeah,
yeah, definitely export it. This is how I did it. Or I started using this app for just like note taking, and then
like during courses or whatever.
Yeah,
right?
and then it's realized it's easy to keep.
Okay, yeah, that works.
You can make like nested pages and stuff. So
it's almost like your own wiki or something. Or,
yeah, you can like write really bunch of stuff.
It's called Notion.
It's called Notion. Yeah, there's lots of templates. I just do it very simply, but
you can also like word processor, or you can paste images inside.
You can put images in. What else can you do? Oh, you can also publish like it as a website.
Oh, so you can make them accessible to other people if you want. Yeah.
I'm not sure, but you can definitely share. Like you have a link of the Notion site.
I guess an alternative then for like regular campus people who use like a GDoc or something then I guess. Or...
Yeah, it's basically like that. But the Google Docs is really how to like code.
Yeah, that's right. So this does like it makes it like a nice box, and then do you get like the highlighting and stuff in there or whatever, like the syntax coloring or yeah. Yeah, that's nice. Okay, all right, we're in the home stretch now. Okay, this is sort of the best part. Okay, so we've already done this because we've got live sessions right now already, but you need to bring in the part 3 files. So CD to your scratch space, the top level, where your W1c is a subdirectory, and then run this command, which is a very similar copy command as we ran yesterday to copy in the additions for part 2 into your directory, except now it's the day 3 adds get merged in. And unlike yesterday, where there should have been nothing, no conflicts, everything we added yesterday didn't exist before. But because I had to correct one of the shell scripts because of the Python VM business, you're going to get one message today that you're going to overwrite something that you already have. I mean, I could take away the -I and it wouldn't ask, but I want to also just show you what CP looks like with the conflict. So the I means if I'm about to overwrite something, let me know. So I think there's a shell script that is going to ask, do you want to overwrite? Because we need to update it. So I'm going to hit enter here, and you see CP overwrite W1c / bsalign1 part.bash, and you see question mark. The two canonical responses are Y and hit enter, and that says yes. And you can say N, enter, and that says no. Or if you're completely freaked out, you can Control C hit and abort the copy. Although it would only realize this, it would already start if it turns out that the way this works, this happens to be the first file CP is trying. If this was something not CP didn't discover until the middle of its business, if you say no or abort at that point, it doesn't undo magically the copies that have already happened. You're just aborting the process in the middle. But anyway, that's what CP looks like when with the -I and when you have a conflict. And in this case, the answer is yes, I do want you to replace the destination file with the updated file. So the main thing that should have given you is this directory job arrays, which is the stuff that we're about to do now. So we're going to CD into job arrays. Okay. So everything that we've seen so far actually works pretty well. So what you've seen so far would allow you to, for example, handle the unsplit files, but probably like one sample at a time, because the unsplit files would be 40 times more parts than we have now. So it's like 10 parts of 20 parts of file right now times 40 would be, well, that's actually already like, it was 800 parts or something. Anyway, actually, maybe that's already even a little troublesome. So, but everything we've done so far actually scales pretty well. I'll tell you where the bottleneck is in everything we've done so far, and that is the for loop over Q sub. That is the weak link in everything we've done so far. That for loop over Q sub is totally fine for dozens of parts. But two things. First of all, you saw it takes quite a few seconds per Q sub, which adds up if you're doing like thousands of them. Okay, so that's disadvantage. Second of all, you're only allowed, I think, 500 job entries in the queue at a time. So if you have a really large number of parts, you can't stick them all in the queue at once. And third thing is, if you routinely flood the queue with tons and tons of jobs, the administrators don't like it. It's essentially because the queue system's job gets harder for every job that's put in the system. There's a lot of overhead per job. And especially if your jobs are very short running, like if your jobs are like a minute, run a minute, if you're putting in thousands of 1 minute long jobs into it, I think they even have an automated system that realizes you're doing that and throttles you down, or maybe even forbids you for a while. You just get anyway. So, and the reason is because there's a better way of doing it than that. Okay, job arrays are the better way. So to really scale to hundreds and thousands of jobs, we have to switch to job arrays and not one queue job per task to do. When you have a huge number of related tasks, the job array is the right thing to do. And the job array counts as only one entry in the queue and only consumes sort of queue and scheduler resources equivalent to one entry. And so it's much easier on the queue system. It's easier to manage for yourself because you don't have your queue list isn't gigantic. It's instantaneous to queue a single array job, whereas the force queue loop can actually end up being hours once you get a large number of jobs. So there's lots of reasons why you want to, when your number of jobs gets into the hundreds, you've got to switch to job arrays. Job arrays also work perfectly fine for small numbers of jobs. So they just kind of you can do everything with Java arrays. You don't have to really use the non-Java arrays much at all once you get into Java arrays. So yeah, so there's another problem though besides that, the scaling problem of for loop over Q sub. So Java arrays take care of that problem, but there's another problem, and that is the for loop over Q sub isn't really that flexible. It's very good if each job only needs a single parameter that varies, like a file name or something, right? So in all the examples we've had so far, when we repeat a job, the main parameter, the only parameter that's really changing is a file name, one file name, okay? And that's really easy to do with the for loop because you can just do for, and then the list of things that vary, the one thing that varies, you just put all the options in the for loop, and then you say do, and then you put in the body, and you use the for loop parameter X or whatever it is in there, and then which is in the Q sub somewhere, and then done. And that works fine. But what if you have multiple parameters that need to vary per job, right? Like maybe it's paired end reads, and you need the file name of the end1 file and the file name of the end2 file, and then that changes together with every job. Or you can imagine, I mean, lots of pipelines have situations where there's multiple parameters, and the way those parameters get set has to change in some coordinated way for every job. The for loop doesn't work very well in that case because there's no like a for loop over multiple lists simultaneously or something, whatever. So we need another thing to solve that problem. We need something that's more flexible with how parameters are handled in terms of matching up what's varying job to job and how you get those into the work script. And we will solve that problem with a template of these very flexible, reusable, and scalable shell scripts that we're going to do. And we'll start with the toy example that you'll see just kind of how easy this system is, and then we'll show you a fancier. We'll redo the alignment stuff with this system, and I think you'll appreciate it. So what are job arrays? So it's very simple in practice, really. Q sub takes another command line argument called -t, and -t, most of the time you use it, it takes a single parameter after the -t, which is usually an integer, a hyphen, and an integer. So let's call that x-y. And almost, a lot of the time, x is equal to 1 for these things. And those are called task IDs, okay? So in our case, for our alignment job that we have right now that we just did, the probable task IDs that you'll choose, the most logical set to choose is 1-42. All right, I want task IDs 1 to 42 because I got 42, what used to be 42 jobs, but now they're going to be 42 tasks or sub jobs of the array job or whatever you want to call them, doesn't matter. But we got 42 things to do, and you might as well number them 1 to 42. So the way we activate Java array support in Q sub for like that situation would be -t space 1-42. So what does that do? That means that in the queue, you will see only a single entry. And in that last column, which is called task ID or something, it's like if you do QStat and you do less, and you see like this last column, JA task ID. And if I scroll down here, you see some things have an entry in that position, but I want to find somebody that's waiting. Those are all running jobs. And of course, they're only going to have one task ID. But let's find some waiting job array jobs. Oh, there we go. There's some waiting ones. Does anybody have like a really crazy one? Let's see. How about this? Anybody got a crazy one? There's a slightly more interesting one. So like, you see there's actually multiple ranges there. I'm sure somebody has one with even more craziness. I think this morning there was one that had like a line that was like this long. But what those are job array jobs. So there was one there that was like 1 to 100. Oh, here's like 1 to 1, 1047 colon 1. So this would be like the x dash t x dash y dash t y dash 1047. What's the colon 1? Well, you're also allowed to step by other than 1. So like if you wanted to do only odd numbers, you could do like 1 dash 1047 colon 2, and it would go by 2 each time. So you get 1357. Almost always that's going to be colon 1 and so on. Somehow just when QStat shows you the listing, it almost always sticks the colon. It's not like if colon 1 it omits it, which is the default, but That's all that means. And you see, actually, you can give like commas, you can give multiple job IDs that don't have to be consecutive. You can give like ranges with commas and stuff. But that's how the job array is going to look like in the queue. It will be a single entry, queued waiting, and it will have in the last column the x-y that you asked for. And then what happens is that when that job array is really a placeholder for like a set of individual jobs. How many jobs? Y minus x plus 1, right? So if you do 1-42, that's 42 minus 1 plus 1. You know, when you have a numerical range, x to y with the endpoints inclusive, the number of things in that range is n to minus start plus 1. So 42 minus 1 plus 1 equals 42. So that single array, entry in the job queue is really a placeholder for like 42 virtual little jobs, one of which is task ID 1, which is task ID 2, one of which is like task ID 42. But they're all rolled up and they're all kind of hidden in that job array job. But when that first guy in the virtual list is ready to go, like when the scheduler found a place for him, that turns it from a virtual job to a real job. Okay, it gets promoted, and you'll see now an actual explicit entry for that, and you will see in the last column a single task ID, which is the guy that's running. So the first one is going to be number 1. So you saw that there with the qstat-l of other people, right? So you see some of these, like this is task ID 409 in this guy's array job. And this is now a running real individual job of his batch. Let's find some, like here, A. Stefan. He's got a whole lot of job array. He's got a big job array job in progress. And you see here job IDs. It's probably a pretty big array job, right? Because its job IDs right now are in the 7,000s and they're still going or whatever. So, and you see, 7643 is running, 7651 is running. If we kind of highlight him, and find out where's his, are they all launched for him, or is he still got a job array? He still has a job array. This is queued waiting. This is the parent job array job that's kicking those out. And he still's got jobs 8,009 to 10,000 have not yet started. Okay. So as the job array job kicks off the guys into real jobs, the job array job gets smaller. Okay. So then the job array, once job array job 1 to 42 kicks off number 1, and number 1 becomes a real entry, the job array job becomes 2-42, and so on, until the job array has kicked off all of them, and then the job array job himself will go away. Okay, and that's the life cycle of these things.
See how cool I thought. I know Peter, Rob, Lauren.
Yeah. Well, we can do clever things. Like we could do qstat and we could use awk to pick out, what is that column? The person is in column 4. 1, 2, 3, 4. That's the person. We could sort unique-c, reverse numerical sort. So who has got the most jobs in there? Right. That's the histogram of rows of usernames right now. Right.
Yeah.
So.
File number.
Oh, okay. So, and you mean that's got to be like millions of files or whatever, right?
He wants it in a file for some reason. And I was
file systems hate large numbers of tiny files. They hate large numbers of tiny files. Anyway, so yeah. Okay, so like I say, the job array job only counts as 1 row in the queue. You have a 500, I think it was my resources we did on day 1, right? My resources. And at the bottom of this, it should tell you your limits. Okay. 500 rows in the queue. Maximum number of tasks per array job, 75,000. So how many jobs could you really have in the queue? 500 times 75,000 if they were all maxed out array jobs, right? And that's a way bigger number than 500. So job array jobs are really what you're encouraged to use. And so the only question though is, how does your work script know what to do? Because when you give the command line to qsub with an array job, and you name the script and command line parameters, when those subjobs or tasks kick off, it's the same command line every time. So how the heck is the work script supposed to know what it's supposed to do? Like, where is the variable? Where's the number that tells you what job you're supposed to do? And then how do you turn that number into the set of parameters you need to actually do something, right? Because that's just an integer. That's not a file name yet or whatever else you need. So that bridge is what the SGE underscore task ID, this what's called an environment variable. You don't really have to care what an environment variable is, but it's a in Unix, it's a property of each process. They have a set of environment variables. Those get inherit by default. What happens is when a process starts another process, like when a shell starts a subshell or a program, the environment of the shell gets passed as the environment to the child. And the next thing to know is that by default, shells, when they start up, import their environment into shell variables with the same names and same values. So basically, this SGE task ID environment variable, whatever an environment variable is, turns into an honest to goodness shell variable by that name, which contains a single integer, which is your current task ID. And it means in your work script, you use that shell variable to decide what to do. Now, again, we still have to bridge the gap between that is just an integer. How do you turn that into a useful set of varying parameters like file names or something? That is what the shell script template I give you does, is it allows you to collect the variable parameters into like a table, like a tab separated multi-column table where rows are going to be jobs and columns are going to be your variables. That's something you might make in Excel or something or whatever, but you'll put that in a text file, which we'll call the config file. And these shell script templates I give you are going to be able to use the SG task ID thing to pull out the right row of that file and load up a bunch of shell variables with the columns. And then your work script body, where you finally get to the part that's actually going to do something, can use those shell variables as the programmable varying parts of what's going on. So that's the setup. And let us start with a minimal kind of toy example just to see how that works. So inside here, there's mult minimal, and you see some files here. Now they're shown fairly pretty on the slides, so I will show you these on the slides. But like you can start to look at these like with cat, right? You could just cat any of these files and you'll see them or whatnot. But they're all here. They're the same thing that's on the slides, but the slides have been colored nice and organized nice. I'll show them to you on the slides. Yeah, we're doing the minimal toy example first. The first thing to look at is the toy examples config file, okay? The config file contains 3 columns and 4 rows because this, what's the little multiply toy example demo that's going to have? We're going to assume there are 3 parameters for every job. The parameters are an integer, another integer, and an output file name. The job of each job is to write like a little message to the output file name that says integer1 times integer2 equals the product, whatever it is, like 2 times 3 equals 6. And I want that in the output file name. Okay. And then we've got like 4 rows here. So we're doing 4 jobs. Okay. So this is just a little demo just so you can start to appreciate the structure of this thing without having a complicated pipeline to worry about. The pipeline here is like a one-liner echo command. So the config file, the way I decided to do it is you do 1 row per job. The columns are the things. The columns are tab separated, and you have to be very precise. If you have extra white space, like spaces around, those will become part of the values. That's needed for full flexibility and so on. So you want to be fairly careful that it's like 14 tab 2 tab file name enter with no extra junk. It's a little hard to tell because spaces and tabs are kind of invisible, right? So it's like, how do you know that that's kind of like exactly what's in this file? Because the terminal emulator tabs over and you can't really tell, like, is that spaced over or tabbed over or what? There are ways to see that. We'll do that in a second. But the first slide here is just showing you like literally what's in there, right? Like very explicitly, there's a single tab here, single new line here, no extra spaces or anything. So that's a little visually hard to read. So this next slide just tabs it out to columns more like it is. And then the next iteration is just not show the tabs at all because we kind of know they're there. And so we just say in a comment, 3-column tab separated, no extra white space, but this is what that means. How would you, you may be in a situation where you have to sort of test whether your file is like that. Here are 3 ways to kind of see the invisibles in it. You could do cat-A. That shows you all the hidden characters. Tabs turn into control I's, and end of lines are explicitly shown with a $sign. How do you know tab is control I? Because in the ASCII code, man ASCII will show you a little table. Tab, horizontal tab HT, is octal 11.9 hex 09, and it is I in the control world. It's control I. So that's one way to do it. You could do the sextump thing. Let me show you the Vim way, because that's actually kind of cool. I could edit in Vim that file. And at the moment, it just looks like you kind of can use your arrow keys and move around and see, oh, that's got to be a tab because my cursor jumps like that. But then if you do this kind of magic stuff, colon set list chars equals tab colon greater than period, hit enter, and then colon set list, and then hit enter, you will see you activate invisibles mode. And you see, it's probably hard to tell on the projector, but actually this is in blue. So it's not real text. And it's a greater than sign, which is what we told it to turn tabs into. So tabs are now like these greater than sign dots, and they're in blue, so you know they're not really there. And now I could see, for example, like if I had 2 tabs there, or if I had a tab in a space, or if I had an tabs. Suppose I could have a tab on the end, and you'd see them. And so anyway, this is one way to kind of see invisible stuff. So okay, we got a cruise. We got half an hour. Here are all the files on one page, okay? So this is the config file you just saw, and I've color-coded everything. So the red column, the first integer, everywhere you see red, that is sort of the data flow of where that's showing up in the scripts and stuff. And the orange number is here, and the yellow stuff is here, and the purple 3 columns is here. And the output directory here in light blue is here. So the color code is showing you where the same stuff is living in different places. So the flow of scripts is like this. The launch thing, which isn't really a script, it's just a plain text file, because this is like literally the command you're going to give in the interactive session to kick the whole process off. This is the analysis launch command, okay? That will invoke what we call the submit script. Okay, the submit script is the one with the Q sub in it. Okay, so the submit scripts thing is to do a single Q sub of an array job. Okay, here is the Q sub, here is the -T, activate array job. Okay, the work script, okay, is the one that actually does the pipeline. Okay, this is the one that starts up for every task that the job array job launches. So in purple here is the actual place, the only place where, like, the whole purpose of this thing is to get down to like this line or what, and you put here whatever your pipeline is. But the advantage is that you get to use all the shell variables in that thing. And then the rest of this is all basically structured just to kind of get those shell variables going and get each of these tasks running on some compute node, right? So the way it works is that let's follow some of the flow. So the submit script takes 2 parameters. The first one is the config file name. Why make the config file name a parameter? That way you can put in different config files and get different things to happen. So for example, you can have a config file for pass 1. Then when you find out things fail, you make a config file for pass 2, and everything can just live in the same directory here or whatever. Your config files can live in the same directory. We actually then make the next command line parameter be the output directory. And so we can have all the script structure, scripts in the top level. We can have config files on the top level, but then we'll have a subdirectory per pass for the output files or something like that. It's very nice. So yeah, so that's the 2 arguments here, the config file and this. So in practice, like oftentimes that might be a pass 1 config file, and this might be a pass 1 output directory, something like that, because then you can do a pass 2 and stuff like that. Okay, now we're into the submit script. Well, first we capture those 2 command line arguments that are coming in from the launch. And then I parameterize some of the stuff here. Like I actually made the name of the work script be here instead of just embedding it here or whatever. This just kind of collects everything you might change in one place rather than you got to dig through this long Q sub command to find it. So this just is the name of the work script, which is this guy. And this is the job name. And it's perfectly fine to give the same job name for all of these. And I think the way it works is that the files will have names like job name dot job ID, but then after the job ID, there will be a period, and then the task ID will be after that. So I think all of the jobs in a job array job get the same job ID, but the job ID really comes in two parts. It's now a decimal thing where it's like job ID dot task ID is the unique identifier for these guys, and you'll see that in the file names and stuff. So we can just leave these all with like one constant unchanging job name. There's really only one job. It's the array job is the way it really is. Here's our resources. Here, this is a very tiny test. So 1 core, 2 gig of RAM, 10 minutes, or whatever. These are just trivial jobs. Here is, we do a word count the number of lines in the config file. Why do we need to do that? Well, that's the number of jobs we need to do. And when we do the -t x-y 1 to y, we need to know how many jobs we need. Well, rather than make you put that into the submit script or something, the submit script can just count the lines in the config file. Right? So that's an easy way to get the number of jobs into the script without you having to specify it. So this is basically just word count lines in the config file, so that then we can pass that to -t in the QSub. Okay, and the last bit of business here is to deal with the output directory. Maybe the output directory doesn't exist yet, so we do in makedir -p. If that directory exists, it won't do anything, and if that directory doesn't exist, it will create it. And then if the creation failed with a double ampersand, we won't even try the QSub. So we make the output directory, and then if that worked, then we try the QSub of the array job. Then the work script, at the moment, the work script takes 2 parameters. It takes the config file as 1 parameter, and it takes the output directory as the 2nd parameter. So now we're looking at the work script. Work script's got some logging, as we always do. It captures those 2 parameters we just got from the submit script. And then here's the magic. Okay, so if we have to pull out the right line of the config file and load up some shell variables with the column 1, column 2, and column 3 value, how do we do that? Right now, I give you this black box scriptlet. It's not a full script. It's something you source into this script, and it's a bunch of script lines. This file never changes. This file you don't need to edit. It's always the same. We can call it a magic black box for the second. There's not much magic in it. You'll see that in a second. But this is basically, you just keep it along with, this is like a file you copy 1,000 times and just use it every time. The way it works is you say source, and then the bashlet, the little scriptlet here, and it takes 2 parameters. The first parameter is the config file name, and the second parameter is how many columns are you expecting? Here we're expecting 3 columns. Now, if you put a 0 here, it will auto-detect. The purpose, though, of explicitly saying how many columns you want is because that will activate much more strict error checking. And if your file if your file sometimes has 2 columns and sometimes 3 and whatever, if the file isn't correct, then you will get error messages from this little helper script that says, I'm trying to make 3 parameters for you, but the file doesn't have 3 columns in this line, so you got your files broken. So this is just helpful because it makes it more strict about the config files that it will accept. So the script doesn't look like it has any output, but it's actually done something for you. It's created a shell variable, or more properly, a shell array, and we haven't done shell arrays yet, but basically shell arrays are shell variables that can contain multiple values, and like other languages like Python and R and whatnot, shell arrays are indexed. And so there's a 0, and shell counts from 0 usually. So position 0 is the first element, position 1 is the second element, position 2 is the third element. And so what it has done is it has loaded up the columns into the shell array params, and you can pull those values out now, and those are your variable parameters that came from the config file. So the 0th parameter, the first column value, we can put in a shell variable integer 1. We could use them like this, but that it's horrible. You want to rename them to things that make sense to you. So we pull out column 1 and we call that integer 1. We pull out column 2, we call that integer 2. And we pull out column 3 and we call that output file name. At that point, we are ready to do the main meat. What is the main meat? It is echo integer 1 times integer 2 is shell arithmetic, integer 1 times integer 2, redirect output to output directory / output file name. Okay. And then we've got our final logging. Okay. So let's run it. Okay. So I am in this minimal example. And the launch text file is the reminder of what you give as the shell command in your interactive session to kick the whole process off. Okay, so I will copy and paste that and hit return. Your job array has been submitted. Let's look at our QStat. Minimal, queued waiting, 1 slot per task. It is a job array job, 4 subjobs. Those are very tiny subjobs, so they should really be pretty easy to place, and they run pretty much instantly. So we're probably not going to even catch this in the running state. It's just going to go from QW to disappeared, because probably all 4 are going to start at once, whatever the scheduler doesn't like work. The scheduler works in rounds, and there's like maybe once a minute the scheduler does stuff. It doesn't like, it's not like every second the scheduler decides what to do. It kind of has batches where it sort of like figures out what to do for the next cycle, and cycles are like a minute or something long. So this is why, oh, gone. Okay, so yeah, so it probably all 4 of them. The scheduler finally started another cycle, found places for all 4, bam. They're so fast, they take like sub-second to run, so they're already disappeared. We never saw the intermediate states. Well, we need more complicated pipeline before we see something. What do you see though? We've got an output directory. And what's inside there? The Q system log files and output log files. This is the output of our little pipeline. So if we look at like some of these, okay, 1, 2, 3, 4 times 5, 6, 7, 8, 9 is 700,77626. Okay. And so on. So if we looked at all of them, they look like that. If we look at the non-empty log files, they are the standard output of our script. That's the begin and end messages from our script. And we don't have any other messages. So hopefully that kind of feels kind of cool, because I mean, although the pipeline is stupid, the structure is pretty cool. So the next thing is the mult template. This is the directory that basically I recommend you copy when you want to start a new job. Okay, this is sort of like the template. You just copy and then you edit these files, whatever. So of course, when you copy these files, you want to change the directory name, and then all these files with the mult template in them, you want to probably rename these files and stuff. But so what does the template look like? So here is the launch and submit. The next slide is the work script. And then the last slide is the config and some comments. But I've colored things in here. So the colors are what you need to edit for various purposes. So like, you know, like these are, I will call variable parameters. Okay, these are parameters that change job to job. Then there are parameters that don't vary across the jobs that are the same for all jobs. I'll call those constant parameters. So for example, the output directory is a constant parameter, right? It still changes, like the launch script, you can put a different value there, but from the point of view of the job array, it's the same value for the entire duration of the job array. So I'll call that a constant parameter. Now you could put constant parameters in the config file too. There's nothing stopping you from making another column and just making the value in that column always the same. That's fine. Depending on how you are doing things, that's either what you want to do or kind of annoying. Most of the time you want a constant parameter, you only want to have it in one place. And you'll have choices for where to put that. Like sometimes it makes sense to put the constant parameter in launch. Sometimes it makes sense to put the constant parameter in submit. Sometimes it makes sense to put the constant parameter in work. And sometimes it makes sense to put the constant parameter as a column in the file. You can put them anywhere in any combination. It's all up to you, whatever makes sense to you at the time. But basically, everything I color in red is related to variable parameters. Everything I put in yellow is related to constant parameters. Everything I put in orange is related to resources, RAM, cores, time. And then things in blue are the setup stuff like module load commands, and things in purple are the actual meat of your pipeline, where the whole point is to get to the purple. The launch command, the general launch command looks something like you call the submit script with a config file and probably an output directory. And then possibly, if you like, you can, this is a place where you could put some more constant parameters in here if you like. And then you haven't seen it yet, but you may also consider automatic construction of the config file. We'll see that as soon as we get to the next demo, which is to do our bisulfite alignments with this system. You can often construct the config file automatically with a shell command. For example, in the bisulfite alignment, what is the config file? It's probably just going to be a single column, which is all the file names we need done. And we already know like the ls-1 command can very easily give us a list of file names. So we can do ls-1 with some shell pattern that finds the file names, and that will just spit out a one column table of all the file names, and we just save that as the config file. So we can actually have the config file be built with a shell command, and that's kind of nice. So the red text here is just to remind you that, well, you could use a shell script, or you could do some shell commands to construct your config file. Another alternative is you could use Excel to construct your config file. Maybe you've got a table with sample IDs and file names and whatnot or whatever. So you have a table in Excel, which has got rows for things you need to do and columns, which are the particulars about that guy. And you save that from Excel as a tab separated file. It's one of the file types that Excel can export for you. And so maybe your config file comes from Excel. The red text just reminds you that's an option. Actually, I don't think the red text appears in the files on disk. It's in the slide, but anyway, you know now. So then if you look at the submit script, how does the submit get start? Well, the submit script has to dovetail with your launching. So if your launching has got these command line parameters like this, you got to modify your submit script to match the same thing, right? So the config file is first, probably you've got an output directory next, and then if you've got constant parameters that you decided to put at the launching level, you got to capture them here in the beginning of the submit script. I always recommend that not just using the positional names. The only purpose for the positional names is to immediately rename them something that makes sense to you. And especially if you then have to renumber like the argument order or something, you've only got one place that you've got to look at. And like I say, if you kind of get long scripts, you'll never remember what 1, 2, 3, 4 are. Just immediately rename command line parameters with things and names that make sense. You could also put resource parameters like RAM and stuff. You could put those at the launch level if you like. If you like, the resource parameters are often just constant parameters of their own. There's not really a distinction between resource parameters and constant parameters. The distinction between yellow and orange here is kind of artificial, and you can put those any place you like too. In this particular way, the template starts, they're actually all the orange stuff is written as is constant parameters in the submit script, but you could distribute those in other ways if you like. So maybe you want to add in more constant parameters in the submit script. Well, you could just put them here, say. Maybe you want to start talking about the resources here, or you distribute them to other places like we just mentioned. This stuff doesn't need to change. The only other thing you might need to change is the parameters you pass to the work script. So in particular, the work script should get probably the output directory, and then the work script probably is going to get all those constant parameters you've been collecting to this point, right? Now, this is also a place where like sometimes like the resource parameters, sometimes the work script needs to know those or know some of those, sometimes it doesn't. So again, maybe you're going to pass some of the orange stuff here too or not. It just depends on whether the work script needs to know the orange stuff or not. But the orange script stuff is really just constant parameters. And so you just adjust this stuff here to reflect whatever set of constant parameters you have it at hand right now that need to go down to the next level. Okay, so then we look at the work script, and the work script is, first of all, it just starts with a long comment. So everything in green basically doesn't need to change ever. But again, of course, if the work script has to dovetail with the submit script, so whatever you decided on how to pass parameters to the work script at this point, basically here's the parameters going into the work script here. You got to modify the work script beginning to capture those in the same order that they're coming in from the submit guy. Submit, not directly from submit. Submit is passing them to QSub, and then QSub causes the job array, and then the job array causes individual jobs to start, and those jobs to start up a shell, and then that starts your shell script, and that's where the parameters come in. But it's the same order that they're being passed in from your submit script. So if you like with loose language, you just call the submit script as passing it to the work script directly, if you like. So you capture all of the parameters from submit. If you would like to add some more constant parameters here, you can do so if you like. And then how many columns do you want me to pull stuff out of the config file? In this demo, it's going to be 6 because the template's going to have these 6 columns, okay? So we put a 6 there, but you just modify that as needed. Then you want to rename the 6 columns however you like. So this is param 0, 1, 2, 3, 4, 5, because the template just gives you 5 columns as a demo. And the first 3 are just going to be the style where you decided to make a constant parameter, just be extra columns in the file and just repeat the value every time. I'm just showing you that as a possibility. And then the main compute of this template is still just the multiplication example. So we've got the integer 1, integer 2, and the output file name is the last 3 columns. Then the blue stuff, I give you a place where you can put module load commands and stuff. So there's none needed in the template. So they're just commented out, but this is where you would put your module loads and activates and stuff like that. And you don't even need the source etc bash rc because the little scriptlet guy here is the invocation of the magic black box right here. He already does the source bash rc for you. So you can just get right into module load here and stuff. You don't have to worry about that. He's done that for you. Then in the purple, this is where you put your pipeline, right? So this is potentially a large number of shell command lines here, which is to actually do everything your pipeline needs to do using all of these parameters that we just arranged to get into you. And the template config file looks like this, just 3 dummy extra constant parameters just to show you that's a possibility. And then here's the integer 1, integer 2, and output file name. So this system scales completely. The config file could have 1,000,000 rows, and that's okay. The config file could have 10,000 columns. That is okay. The values can contain any characters whatsoever, except for tabs and new lines, because tabs are used to change from one column to the next, and new lines define the end of a row. So they can't have those values. But other than that, they can have white space in them. They can have white space at the front, at the back, in the middle. They can have special characters in them. It doesn't matter. Okay. This script template and so on is all arranged to give you shell variables exactly as those with values exactly as they're written in the file. The magic backblock scriptlet has lots of error checking in it. And because it's a sourced script, if it detects an error, it will give an error message to standard error, and it will cause your whole script to exit with a non-zero exit code. In particular, when you reach the line of your work script after calling the magic helper, like here's the magic helper call, and now this is the start after that. If you are still alive at this point, there are no errors. If there were errors, you would have already been dead at this point. This thing will not come back if there are errors. So you don't have to worry about that. And like I said, for many pipelines, the number of columns, the number of parameters per job is the same. And in that case, you set this num config params to that number, and that will help you because it will make more checks on the config file. If one of the lines doesn't have the expected number of columns, it will let you know, and that's a problem you need to fix. If, however, there are some pipelines where it makes sense to actually have a variable number of columns. Like, when would that be true? Well, consider the merging task that we have to do, where we have split multiple samples into parts, but probably the number of reads in each sample isn't the same, so the number of parts per sample isn't the same. In our case, the 2 samples do have the same number of parts because the first thing we did on day 1 was to cut them down to 10.1 million lines exactly. And they actually have the exact same number of lines, and they happen to have the exact same number of parts. But in real applications, you're going to have like 20 samples. They're going to have varying number of reads, and probably they're going to have varying number of parts. So when it comes to do the merge stage, you can imagine a config file where column 1 is the output file name, but then columns 2 to the end are all the parts, and the number of parts just varies from sample to sample. So you want a variable number of parameters per job. And in that case, the magic helper script lets you say 0 for the number of expected parameters, and it will just take however many there are in the file and load up the params array with however many there are. And then there's a way to just, like in the shell script, just use all of them in a command line at once. Like when if we have time, we only got 6 minutes left, but there is an example of how that is useful in the templates here. So if you back out one level out of the template directory, you will see this is the alignment example, the samtools sort, and the samtools merge and index example. And in this guy, you'll see a useful use of the variable number of columns per file. This is the magic helper script. It looks kind of long and scary, but first thing is remove all the comments. Next thing is remove all the error checking. So if no errors happen, the script is only this long. And the stuff in lighter green is less important than the stuff in darker green. And so what is the contents of the helper script really? Well, the helper script gets two command line arguments, the config file and how many columns you expect in the line. First thing that it does is count the number of lines in the config file. And then it does tail -n plus SGE task ID read from config. What does this do? Tail takes an option -n, which is how many lines at the bottom of the file you want to do. Unless the number of lines starts with a plus sign, and then it goes to that line in the file and gives you the entire file from that point onward. So +1 means give me the file from first line onward. +10 means give me the file from the 10th line onward. What line number do I want you to start at? The SGE task ID line. Okay. And what file do I want you to pull from? The config file. That then is used as a redirection for input into the shell built-in called read. And read will read the first line of the input. And the -a means I want you to put the results into an array, a shell variable, an array of this name. And the IFS tab says that the fields that you are to split the line into are exactly where the tabs are. So the script is not, the helper script isn't that magical, really. It's pretty simple. But by the time you add all the error checking and stuff, it kind of looks scary. But this is it. Okay, we got 4 minutes left. Let's look at the doing like a real task, like the bus outlet alignment thing that we've seen, right? So, okay, let's move into that example. Oh, that popped out of job arrays. So stage 1, BS align parts. Okay, let's look at the launch command. You'll notice I don't have a config file in this directory. And the reason is because we're going to use a shell command, which is recorded in the launch thing, to create the config file. Okay, so ls-1 scratch space, your own scratch space, W1c, and remember we made this directory s runs inputs. That's where we recently collected all the input files to by parts. And then srx star part star fastq.gz, redirect that into a config file. Okay, so you do that, and now we have a config file, and we didn't have to figure it out. Okay, we look at that, it's the list of file names. Actually, they're absolute paths to the file names. That's perfectly fine. So we built our config file programmatically. And then if you look at the launch command, here's the launch. We call the submit script. It turns out the way I wrote this submit script, the first 3 arguments are the resources, 4 cores, 7 gig of RAM per core, 1 hour, 59 minutes for the time. The next parameter is the config file, and then the last parameter is the directory you want the outputs written to. And so maybe we'll actually write this to an out pass1 directory, and we should probably, and in fact, actually, we probably should have renamed this config directory the pass1 config directory. Let's do that. So let's rename this config the pass1 config. Okay, so here we go. Resources config file is the pass1 config file. Output directory is the pass1 directory. And now you see I have an array job of size 42 queued. And, you know, given our luck these days, it's going to be 5 minutes before any of those kick off, which is already past 4:30. So, but maybe you see it all how it works now. So, that's that. So suppose we had to rerun some failed, and we need to rerun some. Well, maybe what I'll do is I will copy config pass1 to config pass2, and then I will use a text editor to go in there, and I will start deleting all the parts I don't need. Or you could have just added the parts you do need, whatever, makes sense. You know, suppose it was those 4 guys got to be rerun. Okay, so now I've got a config file that's just those guys that need to run. Well, now I go back to my launching. Maybe I keep the same resources, maybe I buff them up, whatever I want to do. But now you're going to do the config pass2 file writing output to out pass2. Okay, bam. Okay, now normally you wouldn't have both of these in the queue at the same time because you don't know which parts you need for pass2 until pass1 is done, but you get the idea, right? These will actually work just fine because the input files exist already, of course. So these can both run. It's just we're redundantly doing some work here, assuming that pass1 all success. But anyway, so you see how easy it is to change things up, and and so on. It's a pretty nice way to work, and it keeps the files pretty well organized. Here is the submit script. All you got to do, capture the variables and pass the number of cores into the work script, because we need to pass that to BS bolt online. And the work script, we're just capturing those variables. The database, I decided to make the database is the index reference genome. That's a constant parameter. That's one you could choose to put at different levels of the script. I chose to put it in the work level, and so on. You could have put that be a column in the config file, and then you can have a different database for different jobs, whatever. Maybe your files come from different organisms. Here we have a more interesting setup. We have to do the module loads and the activation of the environment. And when we get to the real work, it's basically just the BS bold align command we've done a few times. It's just, we got to play with constructing the output file names again. And so on, we've done that numerous times, but it's basically just an edit of the template in a way that kind of makes sense. So that's that. The SAM tool sort is a very similar sort of business. It just slight changes. Maybe we'll, in our last minute here, let's look at the merge, because that's a little more interesting, because that's got the variable columns. So stage 3, again, notice no config file, because the config file is programmatically constructed. This is a little more interesting programmatic construction than just an ls-1. What we do is, for our 2 samples, we do a for loop, because that's going to produce 2 lines in the config file. For each sample, the first thing to produce is the output file name that we want the sorted BAM, the merged BAM, to be called. We do an echo for that, and then echo-n does not produce the new line at the end of the echo. So we sort of produce the first value, but then we're hanging at the middle of a line. We haven't finished this line yet, because we then need to do tab part 1, tab part 2, tab part 3, and so on. So then we do a for loop over all the file names that come from this sample, part star, all the parts that come from this sample, sorted.bam, and then we echo tab and then that file name with -n. And so we're building up a big, long text line, which is all the list of part file names for all the parts that need to be merged down. This done means we're done with file names. This echo puts a final new line at the end of that long line. This done goes to the next sample. Then we recapture that in a config file. So if I run this blob, you will see we get a config file, which, oh, did I move things around? Oh, because we haven't done the, we skipped this, we haven't done the input to this stage yet, so the file names don't exist yet. So let me alter that to point to the pre-computed slide prep version, so that yeah, where was that? So we need to, this is set up as if you've done the live stuff all up to this point, and we're skipping ahead now because we're out of time. So the file names where you need to pull from aren't the sruns live. It's like the sruns slide prep, I think, is where we need to pull from, because those are already ready. Okay, and now if we look at the config file, oh gosh, I must, sruns slide prep. What are they called? Oh, maybe I didn't give you the, nah, sorry. I didn't give you the pre-computed ones for those. So anyway, okay. So, we're out of time, but it just makes a 2-line file with the, some name for the merged output in column 1, and then a very long list of 21 file names for the parts that need to be merged into that. Okay, so anyway, so you've got new powers now, hopefully. So you've got all this infrastructure to run even large, say, bisulfite alignment jobs, even thousands of jobs. You can apply the split merge technique to other bioinformatic problems you might come into. You have this template, which helps you set up queue jobs of any size and complexity, keeps your files organized, makes multiple passes easy to recover failed jobs. And then I hope you kind of just learned a lot generally about the shell and command line that is just sort of generally useful as you go about your day-to-day business. There are 3 quick cheat sheets I gave you here. If you're interested, it's kind of like just like little, it's like a little really quick kind of like reminder of like different shell features and stuff that there's 3 alternatives there. And otherwise, thanks for coming. And I guess I will stop the recording.